शैला मॅडम, शैला मॅडम, आवाज येतोय का माझा? शैला मॅडम,
आवाज येतोय. नेट आता रिझ्यूम झालेला आहे.
नाव इट इज क्लिअर, नाव इट इज व्हेरी क्लिअर.
नाही, आता रिझ्यूम झालेला आहे ते. तो म्हटलाय पण म्हणजे ही इज ट्राईंग, कारण एक फायबर तुटलेली आहे रात्री काल आमच्या भागातली.
अच्छा, ओके ओके.
त्यामुळे प्रॉब्लेम आहे, बघूया. सो मला माहित नाहीये, मी म्हटलं उद्या ठीक असेल का, तो म्हटला काय सांगू मी, पावसावर अवलंबून. त्यामुळे बघते मी, कारण रेकॉर्डिंगला फार वेळ जातो खरं तर.
नाही मॅडम, नाही, ते परवडत नाही.
तरी मी 1-2 करून ठेवते, जमेल तसं. आता नेट मिळते तेव्हा, म्हणजे मग ते निदान दाखवता येतील तुम्हाला. आणि मिळालं तर प्रश्नच नाहीये, ऑनलाईनच करता येईल. खरं समजेना, हे पावसाने फार प्रॉब्लेम क्रिएट केलेत. आज आता काय आहे सरांचं?
दासगुप्ता सरांचं आहे ना ते राहिलेलं पार्ट, आणि ही विल टॉक अबाउट सम
अच्छा.
रिसर्च 1.5 hour and then we will have Xilinx Vivado or Kumar sir.
ओके ओके, विवाडो. ओके 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 ओके. सकाळी व्हेरिलॉग झालं का नंतर, कारण मला नाही जॉईन करता आलं.
ओके, मी घेतलं मॅडम एक सेशन आता. आय डोंट नो पीपल लाईक इट.
ओके ओके ओके, बघू आता मला कसं काय इंटरनेटमुळे जमतंय ते. आता तरी क्लिअर आहे.
या इट्स व्हेरी क्लिअर, व्हेरी क्लिअर.
ओके ओके ओके.
मॅडम, तुम्ही अजून एक काम करू शकता, किंवा तुम्ही
बोला.
पीपीटी वगैरे बनलेले असतील तर यू कॅन सेंड, सो दॅट आय कॅन रन फ्रॉम हिअर अँड यू कॅन स्पीक इफ एनी इश्यू इज देअर. थोडं सॉर्ट आउट होऊ शकतं.
पण ऑडिओ सुद्धा सकाळी सर ऑडिओच मिळत नव्हता, थोडस चित्र दिसत होतं. म्हणजे तसंही मी तुम्हाला पाठवून देईल, पीपीटी तयार आहेत माझी, पाठवून देईल तुम्हाला. ते पीपीटी पीडीएफ पाठवू,
काही पाठवा, व्हॉट एव्हर यू विश, सो दॅट आय कॅन रन फ्रॉम हिअर. इफ जर तुमच्याकडनं शेअर होत नाही किंवा काय होत नाही, मग आपण एक वर्क, वी कॅन सी हाऊ वी कॅन वर्क आउट, म्हणजे त्या पद्धतीने.
कारण काय आहे, मला रेकॉर्डिंग जरी करायचं असेल तरी एखादा प्लॅटफॉर्म नेटवरनच अवेलेबल पाहिजे ना.
बरोबर.
तुमचा आवाज येत नाहीये सर.
अच्छा,
आता आला. नाही, आता आला.
बोललोच नाही मी जास्त.
येतोय.
बघूया मॅडम,
होप फॉर द बेस्ट. कारण टॉपिक चांगले घेतलेत मी, म्हणजे लोकांना आवडतील असे वाटतंय मला. त्यामुळे बघू आता कसं होतंय ते.
ठीक आहे, चालेल. Okay, we'll start with this session. Sir,
Yeah. Sure.
Sir, shall we start, sir?
Yes, sure. We can start. Yes, I'm ready.
Okay.
So,
yes.
I can. Okay, fine. Yes. So is the current slide visible?
Yeah, yes, sir, yes. Full screen,
Right.
you can do full screen.
Full screen will come.
Uh,
Okay, shall I start then?
yeah, please, go ahead, sir.
Okay.
You can directly start. Yeah.
I think what I will do is, I'm sorry, in the first half, I can only give about 55 minutes. I could not wait longer because I had another meeting conflict. So what I plan to do is, this time, we will discuss about the law of design where we stopped in the previous, in the morning session. And then after about half an hour, 45 minutes, around 4:15 around, I can then start the discussion on challenges for in the areas of in the area of VLSI and microelectronics. What are the research topics where this possibly you will be able to contribute? With this, let me start from where I left. So we had seen in our previous discussion that it is always advisable to have the most active transition node closest to the output Y when power consumption is an important issue or power dissipation is an important issue. So with that in mind, if we look very carefully here, then, and if I assume that my transistor, that my input B in A and B design, right? A and B design, if you look carefully here, see, this input B is having 1 million transitions per second, right? In one, and whereas this is 10,000 transitions per second and this is 100,000 transitions per second. Then, if you want to normalize it with respect to the last one, which is the D part, right? So D part you're normalizing with respect to D in the first case. So D is this one, which is this one, right? It can be seen that this design A, right? If you look very carefully, design A has the minimum amount of normalized dynamic power. And if you compare that with this thing, it is approximately about 19% of savings which you get. Right? Whereas in the second case, when your A2 is the most highest, sorry, A1 is the most highest transition, then you see out of this thing, D happens to be the most power efficient one because you are able to put A1 next to the ground, right? And B and C are almost B and so B and C are almost the same. D is the minimum, which is C. And the concept was that the highest activity factor, as I have discussed here, highest activity factor should be close to the output. That is what already decided. Now, let me come back to the reason why is it like that. I'll explain to you why we come back to that. Let's say we compare this with this. Now, if your pull down path was to get activated, my input B should be high, and not only that, in case number B, right, input B should be high, or either of the inputs A1 or A2, right, has to be high. Then only your pull down path will get activated and Y will go to 0. However, in this case number C, again the same logically the same principle is applied, and so therefore B is high, and again A1 high or A2 high. But in the first case, B, which is the highest activity factor, is closest to Y. Now, why is it like that? Why do we ensure that the highest activity factor? The reason is, say, let us suppose B is the highest activity factor, then any charge which is accumulated here, CL, so you do CL here, you also have capacitive loading here. This capacitive loading is because of transistors at this and this point. So therefore, if your B is high, then any charge which was accumulated at this particular point has already done half the journey. therefore it has to only wait for either A1 and A2 to go high, right? And that reduces your power dissipation levels drastically, because you have been able to distribute the charge which was initially at the CL value back to say CL1 or CL2. So there is a charge distribution between CL and CL1 depending upon the relative values of these charges. So what we have learned therefore is that it is always advisable to keep the most highest activity factor closest to the output, and this will reduce your charging and discharging of the internal nodes. The second aspect is for reducing short circuit currents is try to make the input transition as fast as possible, right? So the rise time of your input should be very small, right? That will ensure that the region when both your PMOS and NMOS are on, that region goes out very fast, and therefore your short circuit current will be faster. First thing. The second thing is, if you apply large capacitive load, right? So if your CL is very large, you would expect to see that there will be heavy delay or skew in the output. Whereas when the capacitive load is very small, I ensure that this is moving very fast, right? So output is going from 1 to 0 very fast, right? This is going from 1 to 0, and input is going from 0 to 1. Now, when it goes from 1 to 0 in the output side, this current suddenly increases drastically, even when the input is rising. So this is your, suppose, VDD by 2, right? So below VDD by 2, your PMOS is on, and therefore, whenever this goes to 1 to, tries to go to 1 to 0, this is going to 0, and therefore a heavy current flows from, so because VDS is very large, VDS is almost equal to VDD. And as a result, even if you have a small capacitive load, your ISC, which is the short circuit current, it maximizes as compared to the large capacitive load, right? So it's advisable to have a small capacitive load. The cost, what is the cost you pay for it is basically your power distribution. If you look at your delay, therefore, delay is minimum here. However, the power dissipation is also maximum here. And that's the cost of you pay for rise time and short time variations for short circuit current. So if I plot ISC as a function of the capacitive load, you can very well see as the capacitive load increases, the short circuit current also starts to reduce. Right? That is very understandably true also, because as the capacitive load reduces, the PMOS starts to conduct more and more, and as a result, what is happening is that the current peaking is getting higher and higher. So what will happen therefore is, now let me get to you from the point of view of, so this we have learned from our previous slide. I'm sorry. So what we have learned from our previous slide is that if you have a small capacitive load in the output, your short circuit current maximizes, right? Because your VDS is high and you are forcing the transistor to bring saturation. Now, if I increase the CL, then look from the point of view of ISC. This is not from the point of view of capacitance. As you make your CL larger and larger, your large CL also increases the dynamic power. So what happens is, as you move from low CL to high CL, like this, your P dynamic actually starts to speed dynamic starts to increase. Now, another good methodology of reducing this short circuit current is to equalize your rise times and fall times. Please think about it yourself. Why is it like that? So if I'm able to make my rise time almost equals to fall times, we'll be able to achieve almost what you call as the perfectly output time for the case of CMOS inverter in general. This concept is known as slope engineering. What is the meaning of slope engineering? Slope engineering effectively means that if you are able to change the slope of the input pulse with respect to output pulse, the capacitive loading will be changing, and under the condition that T equals to TF, you will have a minimum sort of a short circuit power dissipation. Right. Now let me come to what is known, very important term which we typically use in any digital design, and that is known as transition probability. Transition probability is nothing but the probability that the output goes from 0 to 1. Right? We have already discussed the importance of this quantity, because higher the value, more will be the dynamic power dissipation. So if you remember your initial VD square times alpha times, let us suppose F. So if your activity transition, so even that VD square into probability into F, let us forget about this. Then as this probability starts to increase, right, your this power dissipation actually starts, dynamic power dissipation starts to increase. So if you want to have a transition probability, that is probability of output going from 0 to 1, that will be nothing but the probability that the output is 0 multiplied by the probability of the, from a basic understanding of basic CMOS circuit theory. So therefore, you see, if I assume that the, so let me assume a NOR 2, right? NOR 2 gate. Suppose you have a NOR 2 gate. I also assume that the signals are totally independent and statistically independent, which means that they don't have any dependency. So A and B are right. So the signal probability that PA equals to 1 is half, and similarly PB equals to 1 is also 1 by 2. What is the meaning of PA equals to 1? The probability that that input A is equals to 1 is 1 by 2, and the probability that input B is equals to 1 is also equals to 1 by 2. So why? Because you have equal probability of a 0, 0 or 1 in the output. So therefore, I can write down P out, right, can be written as 3 by 4. Why 3 by 4? Because in the output side of a NOR 2 logic, we have 3 zeros, right, and there are 4 inputs. Total 4 inputs, outputs are there, and we are actually reviewing 3. So I get 0. Is it clear? Right. Similarly, I can write down P1 to be equals to, therefore 1 by. Hopefully it's clear to all of you. And therefore, if you want to find out P0 to 1, the probability that the output goes from state 0 to state 1, you simply have to multiply probability that out is equals to 0 into probability that the out is going to 1. So 3 by 4 is the P0, multiply value of P0 to 1. Is 3 by 16. Right? And therefore, so you can also write down that therefore effective capacitance as P0 to 1, right, multiply, right? So the this is the value of, which means that under the criteria that there is some effective external voltage, that can be written as 3 by 16 of the capacitive load which is available, right? And that is how you define your C effective. Right? We have come to transition probability for various other gates, and they are given this. So they calculated is very simple and straightforward. So I assume that statistically again probable. So the probability that the input is equals to 1 is given as PA and PB, and P1 is the probability that the output is equals to 1. Okay? And after this, you can find the truth table, implement it for NOR 2 or NAND 2, right? And also XOR 2. All these can be done by simply putting this value of P0 to 1 is equals to P0 into P1. And therefore, you see, depending on the logic structure or depending upon the the structure of the logic, which means it's a NOR gate, NAND gate, AND gate, or OR gate, I get different values for P0 to. So this we have already discussed in our previous section. So this we have already discussed in our previous section that 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 it is therefore data dependent. The probability 0 to 1 is data dependent, and it is therefore depending on the various values of inputs which you are choosing and the type of gate which you are choosing. So if you look at the transition probability here of a NOR logic maybe, then you see that it's minimum somewhere here. When what is the value there? Where PB is equals to 1, and also your PB equals to, sorry, PB is the probability that input is equals to 1 is high here, and PA is also equals to 1. And that makes sense also. Why? Because you see, when PA and PB both equals to 1, right, for a NOT logic, output is equals to 1, right? Now, why the value of probability is minimum here? Because since I'm only required to do from 1 to 0 to 1, anything from 1 to 0 is totally segregated. It is not required for our, right? So therefore, 1 to 0 for a NOT gate, right, is almost like has got no meaning. Whereas 0 to 1 has got a meaning, right? And therefore, the value of 0 to 1 will have a different value. That's the reason if you look carefully in the slide here, that somewhere here your p values are almost reduced to 0, and this is because of the fact that your PB and PA are both equals to 1. The probability that the output is equals to is 1 is the lowest there, and therefore you get the minimum value of your input probability there. That's an important point. Therefore, for most of the gates, the input transition probabilities depend upon the data. Not only the logic structure of the gate as well. So the probability of input signal has got a high influence on P0 to 1 can also see. Look at a methodology of logic restructuring, and maybe I'll explain to you from the point of view of finding an activity factor. If you look very carefully, if you look at the first figure, which is also known as a tree topology, right? This is a tree or a chain, and this is tree. So this is highly, I must say, symmetric. Whereas this is, whereas this chain is more of an individual output which I'm talking about. I assume that 0.5 is the probability that the input is 1. Then it will become 1 here, and then 1, then 1, then 1, and 1, f equals to 1. If you put and if you input AND gate formula 1 minus PAPB into PA into PB, then you will safely assume that, say for example, 1 minus 0.5 into 0.5 is 0.25 multiplied by PABB 0.25 into 0.25. So 0.75 multiplied by, so this is your 0.75 multiplied by 0.25 turns out to be approximately 3 by 16. Right? So which effectively tells me that by applying an external voltage, we are able to generate, right, high probability of 0 to 1 transition. That's the values of PA and PB. Right? Have been independently verified as well. However, there's a problem here. And the problem is what is known as a glitching effect in a logical effect. Now, if you very seriously on this graph here, right, any output which is being generated here propagate to F via 2 gates. So there will be minimum 2 gate delays. And therefore, since there are 2 minimum gate delays which are getting added up, therefore, the overall delay is also large. Whereas in the second case, which is basically a tree, right, we have been able to balance the input with respect to the input gates. And it looks something like this, that you have 0.5, 0.5, 0.5 and 0.5 turns out to be 3 by 16 for an AND gate, 3 by 16 for an AND gate. These two are inputs for the subsequent AND gate, and the value of that will come out to be some factor depending on the value of the input probability. However, if you see, you clearly see the amount of activity factor at F is exactly the same of that F here. So we will first of all see what is the disadvantage of the first chain product. What is the disadvantage, and then we will see what is the advantage of the this tree topology. So typically there are two topologies which are available. One is train, another is tree. So I'll explain to you what is tree, and then show to you how a glitch is propagated in a chain. Let me show to you. Let me give an example here. So this is, I've already discussed this point, but I will just go a bit fast in this case. That input reordering basically means the highest order signal to be placed closest to the output, right? Therefore, you see A has got the highest transition probability of 0.5. So shift it from input to the output and to the output of the first stage, and also put your this B, which is 0.2 at a later stage. So it is always advisable, therefore, to shift this to this and then this to this. So more is the activity factor of a particular data bus. Try to insert that at the least stage of your design principles. Now, if you go back to this whole discussion, then as I discussed with you, it is beneficial to postpone the signal with higher transition and make it closest to the output down, which is equals to 0.5. Let me explain to you what glitching is all about in terms of design prospects or design aspects of these devices. Now, what was there was initially, this is a two input NOR. Two input NOR, if you want to find out the truth table, right? So it will be 0, 0, output will be 1. And similarly, if it's 0, 1, it's in NOR gate is 0, I'll get 1. 1, 0, I'll get 1. 1, 1, I'll get 0. So now if say input is ABC is A is 1, right? A is 1 and B equals to, so this column is getting activated. Under such a criteria, the output will be actually flipping from, so the initial stages was, let us suppose 0, and then I'm going from 1, 0, 1, right? In that case, output from the previous stage will flip in this case. However, once this talks with the next generation gate, then here also our dynamic logic is sitting, which is to be also taken care of. It's understanding that the C should amount of activity factor as that of B or A. This will ensure that, say for example, 101 is there, right? 101 is 1, 0, output is C equals to 1. Right? So when 101 is there, this will be 1. Therefore, 1 and 1 will give you 1. And all of that will, Z will be equals to 0. So ideally, I'm getting Z equals to 0. You see? I'm getting Z equals to 0. But suddenly in the middle, somewhere around here, you see a transition that both A and B go to, from 1, 0 go to 0, 0. When it goes to 0, 0, the output goes to 1. But the output going to 1 happens only here. Whereas you had actually changed the design here. So this is the effective delay of the gate, which comes to you by virtue of what is known as glitching. This phenomena is right? And how can you remove the glitching? By making the path exactly symmetrical with respect to each other. So why and how I'll explain to you now using a simple picture. Now, if you look carefully here, or maybe another picture, maybe I will show you. Okay, let me show it to you from this angle. If you look at the first picture, it gives you an activity factor. If you look at the second picture, it gives you an activity factor. And therefore, the best option would be lower the activity factor at the possibility of reduced mobility. And another important point which should be important is that once you convert this chain into tree, right, into tree, then you are making the whole design symmetrical with respect to each other. And therefore, internally, I will always like to get the tree being done for the sake of simplicity. That's what I've shown here in real case, in real scenario. Now, let me example of another NAND gate. If you see that once the output goes high, output goes high to low. But what is happening is, let us suppose it was initially 1, and this goes 0 to 1. Right. So if this is 1 and this is 0, and it's a 2-input NAND gate, then I will get output equals to 1. So out was equals to 1. Out was equals to 1, but now my input goes from 0 to 1. So the out has to go to 0 now. And therefore, what you see here is that out 1 starts to go down. So it tried to come up because of the problem, right? Whereas if you look here carefully, this input to gate number 2 is also rising with respect to gate number 1. But then gate number 1 output is going on falling, right? It was initially high, but then goes on falling. Therefore, out 2 will also vary, provided we are able to achieve a good transition between A and B, or between gate number 1 and gate number 2, right? And that is what we have learned from the basic idea. Now, if you consider a carry look ahead adder, then then you see the sum 0 appears somewhere very early in the design time frame, and then sum 1 appears, then sum 2 appears, sum 3 appears, and then sum 4 and sum 5 appears, and as a result, the last sum is sum 10. So maybe 10 bit of addition is also being possible, but we are restricting ourselves to approximately 3 to 5 bits of operation, and you can see is that addition is pretty fine in this case. We've also seen that there's a dynamic problem, and we will try to sort it out by sending this that try to equalize the path length timing, right? So you need to equalize the path length timing. So whenever a path is there which consists of lesser number of active elements, or the interconnect distance is small, then try to insert slightly larger number of buffers in order to have an enhanced value of the delay, and therefore try to equalize it. This is known as equalization of timing path through design, right? So this is what people have been doing it for quite a long time, and this is done in order to achieve overall system level designing, right? In a sense that there will be no glitching now because they are perfectly symmetrical. So the path which you take from, let us suppose, here to here is exactly the path in terms of delay from here to here. And since the delays are exactly the same, we won't expect to have any relative change in the values of your performance. Okay? So that is what we have learned from here, how to cope with glitching. We now come to the next phase, that how to now go for a low leakage CMOS process. As I discussed with you, there are 4 techniques which are generally done for reducing the CMOS leakage reduction. The first is a stack, right? And and then sleep, and then zigzag, and then sleepy stack, right? So these are the four basic ways of reducing static. The first one is, of course, a stack. So stack is, or maybe can explain stack. Stack is induced reverse bias in cutoff. So what you do is very simple. In a stack, you stack one transistor over the other. Right, I'll explain to you. When you stack one transistor, let us stack one transistor over other, then what happens is that this tries to load the top one in a sense. So it is always advisable to take care of this one first and then come to this particular point, this particular transistor. Right? What is sleep? Sleep is basically you disconnect your VDD and ground, right, when the circuit is idle. Right? So you can just put maybe a simple NAND gate switch, which switches on means it breaks the supply whenever this block does not need to power up any one of my transistors. Right? The reverse is true for other cases. So we have a sleepy stack, and which works at very low threshold voltages, and there is a zigzag method. We'll come to that each one of them individually. Let's look into, maybe I do have a diagram for this one to explain to you. Right. Now, if you look at this sleep approach, what we did is that this is one of the most traditional approaches which people follow for low power design. Right? What we do is that we insert an additional sleep transistor between the PMOS and the VDD, and it's basically a PMOS. And we also inserted NMOS between pull down network and ground. We have to also understand that when the sleep transistor is on, the circuit is active. When the circuit is active, the sleep transistor need to be on, and when it is in the switch off mode or at a low ideal mode, it should be off. We for sure take care of it. For example, let's take here sleep approach design. Right? This is known as sleep approach, and as the name suggests, it's basically trying to reduce the activity factor of one of the blocks by ensuring that pull-up network or pull-down network is not working properly. Say, for example, in this case, if your S equals to 0, S equals to, sorry, so I can write down here, S equals to 0, this will ensure that your S bar is equal to 1. Right, and therefore this will be on, and this will be on, and therefore this down network, and this will also pull network. In the second case, when 1 and S bar equals to 0, then both are pulled off. Right, and when they are pulled off, you will never have a short circuit path, and there will be no less amount of power dissipation. The second state is that there's one problem, of course, which comes into mind when S equals to 1 and S bar equals to 0, that you have effectively discontinued the block from the VDD and power rail, and therefore your block output might be very noisy in nature. Right? So that one has to take care of as far as designing is concerned. That you might end up having slightly larger your floating mode output availability. This is known as destruction of state in the floating output. Let's look at zigzag approach. Zigzag approach is something like this. Here there is no floating output. It is either connected to ground or to VDD. So the methodology is that I have a PUN. This is known as pull-up network, PUN, and this is known as a pull-down network. Right? So when the A value, let us suppose, is equals to 0, it comes out, then this pull-up network switches off. And as a result, when this pulls off, this pulls off. Let us suppose this is 0. If this is 0, then this is equals to on, and this becomes PDN is equals to 0. So this is output is 1, and output equals to 1. It will help me to pull down the network here, and output 0 appears in the into 0 of your output for the first case. So you have a 1 here and you have a 0 here, right? And therefore it is also referred to as a zigzag approach for designing your low power transistors. What is stack? Stack basically means that you stack one transistor over another. So when two transistors are turned off together, it induces what is known as a body bias and Dibble effect. As a result, the substitute leakage reduction takes place, right? So let me come to for the combination of the two. Most of the people nowadays use a stack as well as sleep, and therefore they are also known as sleep stack approach for reducing power. So what you do is, let us suppose you have existing transistors which are big in size. You apply an external, parallel to those, you apply a transistor which is in the on state, and therefore it is able to take the output through the buffer, and your main transistor, there is no current there, and therefore your power dissipation goes down. During sleep mode, sleep transistors are turned off and stack transistors suppress leakage current while saving the state. So one important point is that the state is not lost, the state is saved. Whereas in a stack method, there are chances of it getting lost. And now another methodology used is what is known as sleepy stack approach. The sleepy stack is quite interesting. If you remember your transmission gate theory or transmission gate concepts, so rather than using a single pass transistor logic, what I'm trying to tell you is that let me put a transmission gate in the pull-up network or even in the pull-down network, and simply by charging it from 0 to VDD for a fixed period of time, I will automatically be able to populate the next stage. So if you look at this figure here, diagram here, here I divide this. So my pull-up is basically a PMOS. So having W by L of 6, which is broken into two parts, W by L of 3, 1, and W by L of 3, another one. However, the first 3 is used for making what is known as a transmission gate, right? And similarly with the second case, I am trying to make it for an NMOS. For an NMOS, we try to do it. So whenever it's in a transmission gate, I have ensured that this is there, right? And then this is there. Right, so this is your this is a PMOS, and one of the PMOSs has been converted into this format, where therefore the aspect ratio for individual is approximately equals to W by 3. So you had started with W by 6, you ended up W by 3. So the limitation here is that you have added transistor, and therefore your area overheads are relatively larger, right? So this is what we do, and then we come to multiple VDD. So what we do is we use high VDD for critical paths. So if you use high VDD for critical paths, the delay will be minimized for critical path design, and low VDD we use it for non-critical paths. So whenever you're using a low VDD, you will be actually using non-critical paths, because low VDD happens what, that your delay becomes larger. So if you place a low VDD in critical path, right, it doesn't help you. That means your fastest will be much larger as compared to this one. Now, what can you therefore change in the design phase? First thing is that we can actually determine the critical path. We concentrate high VDD for those paths which are highly critical in nature, and lower VDD for all other gates. And for low VDD, you should prefer low VDD. For low VDD, you should prefer gates that have relatively a large capacitances because W by ratio is a larger, right? So why? Because for low VDD, in any case your current is low because of low VDD. In order to offset that, you require to have gates which are wider in dimensions, and therefore you can have large capacitance loading available. Right. So let me come to the next slide. I'll take about 5 minutes more and finish off this slide. And let me see how it works out. So also we use what are known as level converters. You see, whenever there is a technique which people follow nowadays, that your power rail, which is kept here, this is your power rail, right? This is your power rail VDD. And VDH means is pretty high. Let me say VDD is equals to 3 volt. I'm working with 180 nanometer, and I require a voltage of 8.5 volts. So what I do is that, though I connect this VDD with the source of PMOSes, but what I ensure is that the voltages which run my internal biases, internal transistors, they run at VDD-L, which is a lower dimension device. Fine. So therefore you divide, so you use multiple VDD option available, right? So if you have a gate, if a gate supplies with VDD-L and drives a gate supplied with VDD-H, then the PMOS will never turn off because VDD-H means very high voltage. You require very low voltage to turn on the PMOS. So what we generally do in this case is that we have a negative voltage. We also apply a negative voltage, though not written here, for PMOS, and we apply a positive small voltage for NMOS to save power. Right? It also reduces your overheads. So this is what I was talking about. I'll explain to you. So if you look here, I have a flip-flop. Large number of flip-flops are there, and I have a clock. So these are synchronous flip-flops available with us, and there are multiple paths through which you can go. How does it work out? Choose the critical path, which is there. What is the critical path? Frequency of the clock signal will depend on the path with longest delay. So that which has got the longest delay will be a critical path. How the delay is measured? By measuring the intrinsic delay of individual gates plus the delay of the flip-flop plus the interconnect delay, right? Now, if you want to change that from a critical to a non-critical path, you have to change something else to a critical path. So how will you do that? By applying an external bias to that gates, so that those gates change into you give your VDD low VDD. So once you give a low VDD, the internal dynamics tells me that tau THL and tau PLH will reduce, as a result will increase. As a result, they will be becoming having less delay, and therefore it will shift. So what I'm trying to say is something like this: that my initial path, let us suppose from flip-flop, from this clock to flip-flop, is, let us suppose this path. Suppose this path. Now what has happened is I am able to operate this transistor at a much lower voltage. So once I am able to do that, then there is no change in the functionality, but let us suppose this is 1, 1, 1, and this is also 1, and this is also 1. What happened is that, let us suppose this path, because of reducing your VDDL, converts into 2 unit delays. So this will have 4 unit delay, and therefore the critical path will change from this to this, because this is having a 3 critical delay. This is the 4 critical delays, and therefore automatically.
Hello, sir.
Hello.
Yeah, I think this particular slide is basically to show a difference in the supply voltages to be applied or to deciding the clock frequency. Because what it shows is that the path length between two flip-flops or the path length from the input to the flip-flop, basically it is something to do with the critical path and the highest frequency you can apply to the clock. Is that so? Or with difference in supply voltages?
No. What you said in the first one, that was correct. I added something which was not visible in the in the PowerPoint presentation. The idea was, if you look very carefully here, how do you define a critical path which has got the longest delay? So what I do, I start from primary. Let me say this is my primary input, and I go to the primary output. Up till this much point, I travel. So this is my primary input, and this is my primary output. I move, I add the intrinsic delay of individual gates, and I find that, let us suppose that this is the path. Suppose this is the path which has got the
With
highest
higher.
delay, because the
Okay.
right. So what you can do is that this will give you the lowest frequency.
Yes.
Now let us suppose, I will give you a small insight into it. Let us suppose, sorry, just a minute.
Yeah, but the critical path will not go through flip-flop, no, sir. It will be of the combinational logic. Critical
Yes.
path always will deal with the combinational logic.
Yes, but what I'm trying to tell you is, the second case is that let us suppose this NAND gate, right? This NAND gate VDD, the applied voltage to this NAND gate has been reduced by some technique or other. Then what happens is that this NAND larger delay as compared to the previous case. Or let me more clear, it will be when if I take this NOR 2-input NOR gate. Suppose this input NOR gate VDD applied voltage, I am reducing it. Then what I ensure is that this delay, the intrinsic delay of this NOR 2 logic, will be getting higher. So let us suppose it was initially 1 unit. Initially 1 unit when you are using a high VDD. When you reduce your VDD, it converts to a 2 unit. Then it might happen that rather than this as the critical path, it becomes this as the critical path. So you can change the critical path depending upon your requirement by simply changing the power supply input to the gate at the transistor level. So that was what I was talking about.
Yeah, okay,
you are
got
correct.
it. Yeah, got it, sir.
Correct in
Got
the
it.
sense. Okay. Will not be affected at all. So, I agree with you. So they won't be coming, but I'm manipulating these active paths.
Okay, sir.
So I will just right. Thank you. So let me give you the last slide here, and maybe one more slide, and I explain to you what slack is all about. So let us suppose A and B is there, and both so this is an AND gate. A and B are high, and Y will be high. And so what will happen is that if this both A equals to 1 and B equals to 1, this will be 1, this will be 0. So when this is 0, this will be 1, this will be 0. So the output of G2 will be 0. But if this delay is longer, let us suppose, and by some noise value, this C was equals to 1 initially because of some noise, then output of G2 will be actually equals to 1, and then finally it will go to 0 later on. Right? So therefore we define, there is something known as slack in a critical path. How to define slack is, the slack is basically the difference in the delay between the critical path and the non-critical path. Right? That is how you define slack in a critical path. This slack can be borrowed, can be exchanged, so on and so forth. So you see, when A equals to 1 and B was going from 0 to 1, your all inputs have arrived at gate 1, right? And therefore, Y was going to 1. Now G1 is ready with evaluation when the Y value is going to this particular point, and at this point G1 is ready for evaluation. Finally, so the delay, this is the delay of gate 1, right? Because after this much amount of time, your output has actually gone to 0. After this, when you move forward, then you have to wait till this much amount of time for the gate, because when all the inputs to gate 2 has arrived, because this delay might be much larger than the principal delay, and therefore there will be what is known as a slack. And the slack reduction techniques are there. There are a large number of algorithms to reduce the slack. And that is what I was talking about. This is the slack of G1, which you see in front of you. This red colored part is basically the slack of G1. And this much amount of time can be borrowed from G1 in order to achieve the most optimized value in terms of critical frequency. So, as I was discussing with you just now, I'll just finish my slide with this part, and then we'll go for the other one. That generally, though this methodology is not used nowadays because because of the problems of fabrication, that people don't prefer to have multiple VDDs on the same chip, right? They don't like to have it. The fabricators don't like to have it. So what we do is that, as I discussed with you in the non-critical, if you want to make a critical path critical, apply VDDL, you will be automatically having a non-critical path available with you. Critical path available with you if you reduce your value of VDDL. This is clustered voltage scaling. This is also known as clustered voltage scaling. We can do voltage scaling here. So we follow the Dennard scaling law, and we are able to achieve. With this, I think I will stop here, because after this I will take a 1-hour class on maybe a discussion on this one. And what we discussed till now was the idea of a reduced power dissipation. And my whole topic was going there, but you will automatically see and appreciate that the discussion on a delay and critical path will surely come into picture whenever you're discussing power analysis, right? So I had any other slides. I was not able to discuss those because of the want of time. And maybe we will just now go to the next slide and explain to you. But if you have any questions, please feel free to ask those questions, and maybe if possible, I will be able to answer those questions, and you're free to ask those questions now.
Sir, the delay can always be reduced by introducing a flip-flop if it is a synchronous circuit. That is, if you, yeah,
Yes,
that is, you can, yeah. So, I mean, what we say is that as the power, you try to reduce, the delay increases. But in that case, if the delay increases, perhaps you can, in the architecture, put one flip-flop in a combination, in a path which is having in the critical path as such, I can say. And then the delay also can be reduced. You can get the data at a higher rate also, and it will work.
Yes, you're absolutely correct. That can happen. But the problem is the problem with all these problem is that this should be done in a pre-designed stage. Once you've designed your network or designed your digital logical block, and you have already given to the fabricator, you can't come back from the fabricator to redesign it.
No, it should be in the design stage only.
Yes. And you're absolutely correct. It works very well, in fact. It works very well. In fact, people have reported a reduction of approximately 10 to 15% of delay because of such a change. And this is and the good part about it is that it is not only applicable, it is technology independent. So if you work with 180 nanometer, 65,
Yes.
22,
Yes.
14, 32, everywhere, it works fine.
Okay, correct. So I think maybe whatever you had discussed is at the chip level, and when you go to the architecture level, this pipelining, parallelism approaches will come into picture.
Yes, and it is not only chip level. This is not at the architectural level. This is more so at the
Component level.
gate level, not transistor
Device.
level maybe, but at gate level abstraction.
Yeah, device level.
And then one more thing which I might like to point out, it has been seen that the most saving, the general rule of thumb in industry is that the most saving which you can do in power happens to be when you do it at architectural level. Whenever you do architectural level abstraction, there the saving power percentage is much higher. And as you start going down to a transistor, the savings actually starts to reduce.
Yes.
So you put in large effort, but the result happens to be a reduced result.
Yes, sir.
Okay.
Sir, what about the adiabatic logic?
Yes. I have a slide, but sorry, adiabatic logic has not been successful over the years. And the reason being very simple, that the area requirement is so heavy in adiabatic logic that the gain which you get out of power, first of all, is very difficult in the sense that to offset it. This is the first thing. The second thing is, so area is very high. The second thing is in adiabatic logic is that it becomes to an extent frequency dependent. So let us suppose you want to use adiabatic logic at 2.4 gigahertz window of operation, or if you want to use that for your 5G operations. it will not work. It will not work. Simply, it will not work. Because adiabatic concept is that you do the operation so fast that that the power dissipated is very fast. It gives you a very large power dissipation. So yes, if you work with very slow logic or your logics are not very fast, then adiabatic is there even at the cost of area. But as of now, to the best of my knowledge, is not successful. Few
Okay.
Chinese authors have been doing it, but I don't see any
Okay.
advantage of adiabatic logic.
Okay. Okay, sir. Thank you.
Okay. So I think somebody has in the chat box has raised it, but I cannot read. Can I see? Yes, yes. So Uma is writing, sir, if the rise time and fall time of a power clock of a circuit is increased, then will the power consumption be reduced? Uh, if you want, what you're saying is you want to increase the TR and TF of the clock. So when you increase TR and TF, you actually make the circuit go fast. And therefore, though your delay reduces, your power dissipation increases. So sometimes your dynamic power dissipation increases drastically in that case. And therefore, your power consumption will not be reduced, will be increased. However, your delay will be reduced when you reduce your rise time and fall time. So if you reduce your rise and fall time, TR and TF, then you will be able to make the circuit move faster at the cost of higher power dissipation. Is it okay, Uma? Okay, I hope it is okay. So, Dr. Rathore, shall I move to the next presentation or any questions?
Yeah, sir, you go ahead with next presentation.
Okay, fine. So this will be about 1 hour or so. And what I will be highlighting here is current research trends in emerging semiconductor device technologies and future roadmap for electronic industry. So before we move forward and explain to you anything about it, maybe I will slide here. So I'll just. So these are the few areas which I thought I should discuss with you. So the first two are basically your device level research being carried out across the world, and the next two, in fact, this and this are at circuit level, and more so this is at the system level. So I've chosen such a manner that I will be able to explain to you all the three aspects. We'll try to at least do that. And this is from, so when I say research, especially in engineering research, you need to, the first thing which comes into your mind or should come to your mind as a researcher is that please look from the application point of view. That is very, very important. So whenever you start your research, those who are starting their research now, or those who intend to do research, they need to first of all find out that any research they are doing, especially in engineering research or physical research, that has to be correlated or mapped with the application area. So one thing, as a budding researcher, everybody is there, that you have to map your research to applications, right? There are certain research which need not be mapped to applications, not always, but when you're doing engineering research and you're developing a product, this matching is very, very important, and this can be done by you with the help of your. And the second thing is you do very good amount of what is known as a literature. Initial period of research, you will be able to find out what are the technical gaps, right? And from the technical gaps, if you have these technical gaps numbered 1, 2, 3, 4, 5, let us suppose, then thesis or your work should be such that you are able to plug at least few of the technical gaps, right? This is a general trend. I'm not saying this is the only trend or this is the only way of moving forward, but this is the way which moving forward I prefer to do. There are other ways of doing it, and they are equally are well. But this is what I have been doing it, and I can share it with all of you. So research to an application, do a proper literature survey, because now you have internet at your in your fingertips. Do that. From there, with your help of your advisor and your friends and your colleagues, try to find out technical gaps, and then make an effort throughout your research period to at least plug some of the technical gaps in that domain, right? So this is a general methodology of a research application which you should do, right? So what I will take up now is basically explain to you the various areas of research which is happening. There are many areas of research, of course, and as the name suggests, it is you are searching, you are researching it. Means people have already done some part of it. You are actually researching. So but then don't research then but don't but ensure that whatever you do a research is adding to the state of the art. That is very important. Add to state of the art, right? State of the art. And you should be able to do this at least. Even if you add 1% to the state of the art, I will assume it to be a good idea. How would you ensure that it is adding to the state of the art? No, it's finished. It's done, right? So, sorry. So it adds to the state of the art which you do, right? And how it will be known to you? By publication, by patents, and by system design. Those are, when I say system design, I specifically in the area of data side design. When I say not everybody will be able to do system design, but at least publication patents can be one of the areas. Similarly, conference proceedings and so on and so forth, right? So, but then you please ensure, and I will, those who are advisors here, they're already very knowledgeable people, but then publication only should not be the criteria for the good research. Without publication also you can have good research, and these research can be quite interesting in dimensions without having any publication. I can share with you one small incidence. IIT Kanpur, there was one research in 1900, and I think way back in 90s or 80s or 90s, from IIT, we had a research paper. It was just a 32-page research paper thesis, right? So it is just 32-page thesis without any publication coming out of it. But it was the most quoted thesis in industry by industry. Right? So that type of work, if you can able to do it, then it doesn't matter whether you're doing research based on some system level, non-system level, as long as you're able to add the state of the art. Right? So let me come to the next case, and then let me start with the motivation of the talk, right? And then these are just sort of idea that you will have where we are moving forward. One area where we are moving forward from India is basically in the area of 5G network, resulting smartphone, right? Currently, you have 1.75 billion people using internet across for your data. In fact, it has further increased currently in the internet data. It has increased drastically now in day-to-day activity. What are the core areas where I think somebody is asking some question? I will just let me see what she's asking. Is it just so she's asking how to map the work to an application. If we didn't, okay, fine, very good. So the question she's asking how to map it. So this, there is no exact answer to this question, but I will give an example. Since you raised this efficient adder design, let's suppose you have designed an adder which is which according to you is very efficient. Then compare your design with that of the pre-existing design, and let us suppose you try to find out energy required for 1 bit adding operation, and compare your design with the existing design. That will be a sufficient way to say whether you have increased your state of the art. The second thing is, can we realize it on chip? Because most of us are working in VLSI domain on chip. That's a difficult task, but then can it be done? Yes, it can be done. And if you're able to do it using even 180 nanometer PDK, please go ahead and do it. Sir, we should decide the processor type and then design an adder suitable for it. Yes, if your aim is from application side. So I will give an example. Let us suppose you are working on wireless sensor networks, and you want an IoT which will take the signals from the WSN, wireless sensor network, and try to process it on the edge and give you the result. Then you have to decide what processor type you are taking. Are you taking an ARM type processor? Are you taking a simple Cortex 5 processor? And then what you do is that compare your processor design with that of the presently available literature, and then do an operation, and then for a single operation, how much amount of energy you're consuming, for example. That can be a good figure of merit. Or what is the delay, overall delay between the primary input and primary output. That will be a good design also. Right? So such type of networks you can actually go ahead and do. I hope I've answered the questions. So the aerial view of interdependency information. You just write in a chat box. I will come to that later on once I finish my talk. So typically we use IoTs in most areas nowadays. In basic, the area in which I work in the VLSI domain works on consumer electronics. We have a core facility for cloud computing. Heavy IoT requirement is there, and we require to currently take care of all those things. Now let me come to the motivation therefore. So as I discussed with you that with proliferation, you can read it if you want to, but primarily with heavy computation, right? With heavy computation, both at the data level and at post data level, you require that your on-chip processors should be very, very not only time efficient, it should be also energy efficient in nature, and therefore that has to be taken care of. So one is the hardware side where the research is going on to improve the efficiency. Another is basically the software side or the cloud side, where computation, ways of doing computing is also being looked into. So these are the two basic areas, primarily in a big sense, we are looking into the product. So if you boil this down, go on going down, one thing which comes into our picture is, can we have an ultra low power super transistor technology available with us, which will replace your current technology. So as you're aware, current technology is generally restricted. People have reported 7 nanometer FinFETs they have reported, and some Chinese groups have reported even they fabricated even a 3 nanometer FinFETs in open domain. It is already there. Intel is doing a very hard work on 7 nanometer FinFET. So, but the problem with these are that they have very restricted subthreshold swings and there are certain reliability issues. So can we have a technology which will replace the current MOS technology, and we will be able to achieve much lower power dissipation in the longer run? Right? So that is what people are looking into currently nowadays. So if you look at this chart here in front of you, and let's look at where people are working in a very holistic fashion. This is your application technology, right? Your application technology, and they are mapped. So, for example, I'll give you an idea. Suppose you have an autonomous vehicle application, then research in computer vision can give you the idea to applicate. Similarly, if somebody is working on speed, then that can be also in the intelligent robots in the area of robotic technology, right? Say for example, if you want to develop augmented reality, virtual reality, then intelligent education. For example, today is currently and all these things, they work very well on virtual learning or virtual reality, and so that is one important point. Then one big area coming up with AI and ML is man-machine, and that will give rise to smart city blocks across the world. So and the third thing which many people across the world are looking into is intelligent hardware. Can we have a reconfigurable, right? Intelligent. I have a chip here, right? When my data rate is low, or the baud rate is low, this operates with low sampling rate. I'm giving you a very basic language, low sampling rate. And once the the baud rate increases, I convert this low sampling rate into a high sampling rate automatically. So you don't require external intervention for doing that. Your system will be automatically able to understand and convert from a low sampling rate to high sampling rate by using a configurable logic internally. So here also a large amount of work is being going on. So large on computer vision on image processing will require such type of networks. Right? So these are the few areas which come into my mind. There are other areas also. This is just not the holistic one, but this is the overall area which you see. We come to the, because that's where I work, so I can easily tell to you what the areas are. Must be aware of, those who are working with devices will be aware of that generally the lower limit of subthreshold flow for any FET technology is 60 millivolt per decade, which means the switching activity of any FET device is only restricted up to 60 millivolts per decade. And I cannot go into that because of obvious reasons. This limitation is referred to as the Boltzmann tyranny. Right? So over the period of discussion, you will understand how I can map my research with an application. It will come inherently to you, all of it. Now, what has happened over the years, and this is very, very important, that if you follow Moore's law and if you follow ITRS, ITR is International Technology Roadmap for Semiconductors. The last one was written in 2015, and the latest edition is 2018 also, and 2019 has come. But if you even look at 2015, you will see that if you follow Moore's law, then the rate at which the dimension of the transistor is reducing, your voltage is not scaled in the same dimensions. Right? Because you need to scale down the voltage also, because otherwise the electric field will be so high between drain and source that you end up having destroying the material itself. So you need to scale down your voltages. Right? So the voltage have not scaled down drastically, and therefore your power is going up. The subthreshold slope is only limited to 60 millivolt per decade at 300 Kelvin into 60 millivolt per decade, which means that the switching speed is only restricted by 60 millivolt per decade, and you cannot go below that if you're using a bulk mask. Therefore, can we have some device, right, which can actually lower the switching rate? Now you will ask me, how will I map the application? Well, let's look at the application area. Say you want to sample a signal at 2.4 gigahertz system. Then your sampling rate should be twice the Nyquist criteria, so you have to minimum frequency is around 5 gigahertz. You have to sample the input data. So with such a high sampling rate, you require a transistor which will be able to mimic such high switching rates, and this can be only possible when you lower the subthreshold slope to below 60 millivolts. So now you see, you can limit your applications to your research in this fashion. I agree that it comes with a lot of research, lot of experience, but you need to inculcate it sort of within yourself as a researcher, and this will come in a subconscious manner. It will not come very consciously to you, right? And therefore, typically we are looking at subthreshold slope of approximately 1 millivolt per decade to achieve such large switching speeds, right? Now, conventional MOS devices does not give you that, right? And that's the problem area which you will face for emerging devices. So, therefore, a new physics of transistor is required. So, one of them happens to be one of the most promising research areas which people have been looking into are these three areas where, sorry, these three areas where there we have the tunnel FET, you have NEMS. So this is your NEMS. You must have heard of NEMS. MEMS you must have heard, micro electromechanical systems. We have a nano electromechanical systems. We have from the device point of view. This is from the device point of view. This is from switch and therefore from your subsystem point of view, right? And this hardcore device level device. Based MOS device. I will not discuss too much about this or this. That's not my domain. I will discuss something about effects here. Those who are not in those who are not in the tunnel FET domain, they can appreciate. Like those who are in electronics, just assume this fact that when you are discussing MOSFETs, the way the current is formed in the MOSFET is via inversion of state, right? So what you do when you do an enhancement mode MOSFET, you apply a gate voltage which is positive, and then you invert the channel and make it as much N-type as it is initially P-type. So you have to bring your gate voltage much larger than the threshold voltage of the device, and you're able to invert the channel. However, that's the basic FET device. However, in a tunnel FET, you try to tunnel electrons. So what is happening is, this is my, those who are aware, this is my configuration. If you look at the tunnel side, so this is my gate, this is my source, and this is drain. And if you apply now gate voltage, and if you apply a positive gate voltage, then what you do, you shift this downwards, because remember this is energy scale. So energy is equals to Q into V. Since electron is negative, whenever you apply a positive bias, you will be shifting this down below. Once you shift it, what is happening is that this is already filled, fully filled up, and this is almost empty because you're using an intrinsic type indium arsenide. So this is basically a 3,5T FET. So what you do is, therefore, that now, because of this short distance between two, electrons can easily go from here, tunnel indium arsenide or indium arsenide layer here, and move towards the drain end. Because drain end has got large electron, so, and they're aligned with respect to each other, and you can do it. So therefore, thin barrier and therefore large density of state should be appearing both on the source side and on the intrinsic side for this to happen. Right? And that's what I've shown in this diagram here. That as one increasing the gate voltage, this starts to go down, the tunneling probability increases. But the cost you pay for tunneling diode is that your on-ramps are much lower as compared to your MOSFETs. So this is what I was discussing with you. This is what was happening in a MOS device, and this is in a tunnel FET. So tunnel FET will be fully filled states. This blue one is fully filled states, and this is Fermi levels. So these are empty states, and therefore filled states and empty states are very close to each other, with very small distance between them, and this is known as direct tunneling, which happens in a tunnel FET. Right. So this is the device operation. I will not go into details of the device operation at this stage, but generally tunnel FETs gives you a larger, faster switching. So if you try to find out the slope in this region, right? If you want to find out the slope in this region, this gives you the threshold slope, and this will be smaller than 60 millivolt per decade. Some people have even reported 12 millivolt per decade, which means it requires just 12 millivolt of variation in the gate voltage in order to have a 1 decade change in the current. 1 decade change in current. I think that is, all of you are aware of this basic definition. And people have reported very low values of suppression slope. Heterojunctions have been used. I will not go into details, but this is known as homojunction, which is basically made up of P plus silicon, intrinsic silicon, and N plus silicon. And we have a heterojunction tunnel FET also, which consists of germanium, silicon, and then silicon. Right? In both the cases, you have The only thing is that heterojunction gives you a much smaller tunneling junction as compared to homojunction. But then the cost and currents, cost is very, very high for a heterojunction, especially if you're making using a germanium silicon sort of structure. One was made by University of California at Berkeley, UC Berkeley, and this is actually a TEM for that only. And they reported this was a slightly an old, yes, exactly, it's slightly an old paper. It is VLSI Design 2010, and it gave me 46 millivolt per decade. Currently, the recent trend is around 12 to 15 millivolt is the current trend in at 300 Kelvin. At 300 Kelvin. And and so I will be able to control it. So what they used is that they use divots inside. This happens to those who are aware of. They will help. You can actually do a Schottky diode theory here and have the interface. So what people are trying to do is, so rather than have the depletion region so spread out, if you can have an abrupt junction here, then the tunneling distance will be reduced. When tunneling distance reduces, the tunneling probability increases and the currents are relatively much larger in this case, right? Other experimental techniques have been formulated way back in 2006, that 2008. So 2006 was basically a CNT based, but CNT has not worked very well with us because of the issue of reliability. Stanford did a 2008. Stanford did a strained silicon double gate this thing. But however, the problem was it gave us a very high current or a good threshold slope, but not together. One good idea came out of Hitachi in 2010. Hitachi is a company which is involved in device fabrication, and they a novel TFET device design. And then 2012, Hokkaido University in Japan, they formed a heterostructure-based nanowire-based silicon heterojunction TFET. It was the lowest at that point of time. 2012, it was 20 millivolt per decade. Right? But they couldn't explain to us or to the people how they were able to achieve such a lower value of this thing. So what are the benefits? Let us go quickly over this. The benefits are steep threshold slope. I have a large ion buy-off ratio. So ion buy-off means on current by off current. And this is because your off currents are relatively smaller in this case and very small geometry scales. They're compatible with silicon germanium technology. What are the challenges? The challenges are primarily ambipolar conduction. Ambipolar primarily means the conduction happening on the backside. See, since you're able to conduct here, you can also do a back conduction here, which is known as ambipolar conduction. Right? And that's a major problem area of TFET. Right? So they are most attractive at low voltages, but not at much higher voltages. Let me come to the second type of emerging device which is being reported is what is known as an NC, negative capacitance FET, right? And we'll go one by one. So subthreshold slope is given as dVg d log of ID, which means that the amount of gate voltage required to make a 1 decade change in the drain current. So if you break it up, I can write dVg as d psi s into d psi s upon d log ID. What is the psi s? Psi s is the surface potential. What is surface potential? Surface potential is very simple. Silicon, this is silicon dioxide, and this is silicon. Then the potential available at the interface of silicon dioxide. So let me write for you. Potential silicon dioxide is referred to as surface potential, is written as psi s. This dVg d psi s is referred to as m, right? And d psi s d log n ID is referred to as m. So what does it tell me? That this tells me that with change in the value of VGS, how does my psi s change? So I can simply write down this also as d psi s dVg. So you look at this graph, or look at this expression. It tells me if with how does my psi s change, right? And similarly, with varying psi s, how does my current change? And therefore, this relates basically how does VG changes with ID. We've already discussed this point in detail, right? The psi will be relatively smaller because it is down below the oxide layer. M is greater than 1, right? However, as I discussed with you earlier, N is limited to 60 millivolt per decade in MOSFET. N is this one, right? It's always limited to 60 millivolt. That is for a conventional MOS device. Now, if you look at this diagram, so if you look at the fourth quadrant, is what I was speaking about. Can we have a material whose M is less than 1? Why M is less than 1? M is basically your DSIS, DVGS. Less than 1 primarily means that, sorry, let me just go back to the previous slide. DVGS, DSIS. So it's basically inverse of this one, which is DVGS, DSIS. If it is less than 1, it primarily means that DVGS is less than DSIS. Therefore, for a large change in the VGS value, I will have a relatively small change in the value of SIS. And therefore, I wish to have M and at least N equal to 60 will suffice. However, I can also have a tunnel FET in which M is less than 1, right? So I can do a very fast transition. And N should also less than 60. N less than 60 because of the TFET operation which I discussed with you. And NC will give me M less than 1. Right? So this was one of the examples, and what we did was nothing very extraordinary. That after the gate, which is a metal gate here, this is a metal gate, we introduced at this place a ferroelectric material. Right? As you are aware of, ferroelectric materials helps you to polarize. So there will be polarization of dipole moments, and as a result, you will always have a hysteresis or a change, right? And so what will happen is, so from very fundamental first principles, if you change your gate voltage VGS by certain amount, because of polarization, the will be larger, and therefore you will be able to amplify the change in gate voltage just above the channel of the NC FET, and these are known as negative capacitance FET, right? So people in 2017 have reported NC-based vertical TFETs with very high band-to-band tunneling rates and very large on-to-off ratio, right? And this is one of the very seminal papers people are using by Kobayashi. So those who are interested can have a look into this paper. This is by Kobayashi, and this is published in IEEE Transactions in Nanotechnology 2017. Let me come to some. So we have finished the first part, the device part. We now come to the subsystem part, the system part. Nowadays, with advent of large databases in terms of data analytics, a new area has caught the imagination of researchers, and rightly so, of using artificial intelligence. How can you use it in semiconductor industry? So typically AI can be used in the areas of application. So wherever you have an application domain, this is the application domain where you can use your artificial intelligence, because your video analytics, all your speech recognition algorithms, all your nonlinear programming algorithms, control algorithms, all are governed by basically the concepts of artificial intelligence. But as you go down this green scale from application down to device and CMOS technology, let's look at this particular. So this is hardcore devices and maybe a subsystem level. So people have contributed quite a lot in that, and still research is going on. There's a big way coming domain where people are looking into high-speed GDDR, as well as people are working quite a lot on SerDes, serializer and deserializer, right? If you look at bionic devices, which tries to mimic biological devices, one example is coming up is basically a memristor, right? And people have been working on memristor. Those who are not aware, memristor is basically a fourth organ after the RLNC. If you want to study more thing, you can just type in the Google CHUA, CHUA, and then you put memristor here, and it will give a large number of papers and open domain applications of memristors. Huge amount of work, and our group at IIT Roorkee has also started on what is known as in-memory computation. This is also known as CIM, which basically means compute in memory. Compute in memory. So in I can explain to you what I'm talking about. If you, I don't know how many of you are aware of this von Neumann bottleneck. You're aware of Harvard architecture. You're also aware of von Neumann architecture. You must be aware of what is a von Neumann, but you have a processor and a memory. You bring using data bus and instruction bus. You carry data from memory down to processor, process it, and the process data is again thrown back into the memory. And this happens very often. However, with increased data, the amount of energy you spend just to bring the data from processor to energy to memory and back and forth is so large, or is so excessively large, that now the advantage of von Neumann architecture is fading. So people are thinking of having the processor being done, processing being done exactly in the memory itself, and that is what is known as compute in memory, right? So if you can do a mathematical operation, or if you can do a logical operation where in the memory itself, then we define that to be as a computing memory. So it's easier said than done. It's very difficult to do it in a practical sense, very difficult to achieve it. So that is one area where people are learning. Then there is a group of researchers across the world who are working on language translation, machine-human interfacing, right? And then a large group of people are also working on augmented reality and virtual reality, right? So I don't work on that, but this is all I have taken from open literature, and through my understanding, I have been able to explain to you some areas, some ideas of AI in our semiconductor industry. Rather than going into this, I can actually maybe explain to you. I don't know. These are all. I'll just give you a small time to do it. Yes, so I discuss with you this part maybe, and then finish the talk here. One important area where work has been going on from a higher perspective is edge computing, which means that rather than having uh, uh, computing done at the cloud, can you do it at the edge so that my transfer rates are not there, are reduced, and the latency is reduced drastically. The cost for you, the cost you pay for it is higher power requirement, because at edge you require, if you want to do computation, you require a very heavy power supply to do that, right? You will be like, like surprised to know, those who are aware might be not too much surprised that the Google has its database and its computation center at San Jose in California, right? And there what they have is that they have huge, so the cooling towers are very huge for cooling these servers, because all the computation is done there, and therefore it is very, very high. So the cost, so what they have seen quite interestingly is that the cost to cool down your servers, right, is becoming excessively more than what they're earning out of the data transfer various data centers. So I'm spending more money in cooling my servers rather than on I'm obtaining the money back from the system, and making life difficult. So what people are trying to do is that can we shift these computations at the user edge by providing what is known as the edge computing, AI-based edge computing design, right? And that is what they're trying to do. So some of the important are intelligent robots, right? Intelligent cameras, sort of drone technology, heavy IoT devices, smartphones, and a few of the computing domain analysis which is available with this. With this, so people have been working on transportation, on healthcare, manufacturing, agriculture and smart farm, energy and grid control, and so on and so forth. As I discussed with you, this is the von Neumann architecture or the bottleneck which I was discussing, and this was given in 2017. So it's a very recent and a very new topic. maybe those who are interested can work in this area. And this is what is known as a von Neumann bottleneck I was talking about. This is the von Neumann bottleneck which you see. So the bus is not able to handle the large data, and the amount of energy which the bus is doing or is transferring from processor to the memory is excessively larger. So they are trying to embed this AI processor back into the memory. So you have a conventional 60 SRAM cell, right? You have a conventional 60. Now this conventional 60, can it handle your Mac operation, right? Or ZAC operation? So logical as well as both arithmetical operations can be performed by the 67. And that will open a new paradigm in computing power. So this is the bottleneck I was discussing. You can get this from this reference, which is there in IEEE Computing in Science and Engineering. And as you can see, if you follow 1918 extrapolations, then you would have gone to switching energies of 10 to the power minus 21 by around this much amount of time. But what has happened is that the switching energy does not follow this linear trend. This is not actually a linear trend. This is a log scale here. So this is yes. I think Mohammed Zakir, you can type your comment on the chat box, and then I will be able to answer it once I finish the talk. So, I have a rapid. So you see what has happened is over the period of time, the clock frequency. This is known as clock frequency plateauing, right? Which means the clock frequency by which, say, for example, Intel is nowadays using a clock frequency, but one generation ahead of it, there will be not much reduction in the Intel's capacity. Okay. Similarly with IBM, if you look at IBM and Intel's clock frequency rates, they are somewhere here, the few gigahertz range plugin. And not able to go below this one for some reason or other. And that reason is basically your bottleneck. It does not allow you to go anything below that in a detailed manner. Right? So this is already I've discussed with you. This is one of the examples of the Google. This is Google's cloud TPU pod, and it is a photograph from 2017. And so there are huge such servers available across the network in California. If you don't do edge computing, the problem are you require a very large storage requirement, right? And then you have to handle large, and therefore specifically off-shift memory is becoming costlier nowadays. Right? So with AI, we expect to have some amount of edge computing being done at the user end in order to achieve it. I don't work. Maybe you can have a look into this slide, and then if you are interested, you can work with these in these domains. As I discussed with you, reconfigurable computing technology in terms of architecture, hardware, and using software to change the and to increase reconfigurability is in a big area in which people are working currently. I know for sure there's a good group at TU Technical University Dresden, and I think his name is Professor Weber. Right? Those who are interested can have a look. He works on reconfigurable architecture. Right? And this is coming up in a big way if you are interested to work in this domain. Similarly, if you look at people are actually looking into CNN and then looking into RNN and applying AI chip design here. And if you see here, the below the two figures, they are basically artificial intelligence based chips. And if you see the power and the amount of peak performance, their frequency is not very high. That is just 10 to 200 megahertz. But the peak performance is really excessively large. Right? So at the cost of a reduced frequency, I am able to achieve a very high peak performance, and my power is also not very heavy, and you can actually operate with TSMC 65 nanometer low power technology, and with the ranges supply of 0.67 to 1.2. And this is what I was talking about, the energy efficiency. Some Uma was asking me, and this is what I was talking. So per unit of power being dissipated, how much amount of teraflops of data you are able to transmit. Okay, that is what we're looking into as one of the figure of merits. This is another group of people who are working in the area of emerging non-volatile random access memories and increase the memory size. Right? So random access memory is coming up in a big way, and flash memory people are working, but flash memory is almost saturated in a sense that we don't have too much amount of work going on in flash memory. But NVRAMs are emerging to a larger extent. For example, RERAMs is coming up in a big way. Then again, spintronics based memory is coming up in a big way, and people are contributing there a lot. I think there are further memories, but I will not go into details of this one. I can share the slides later on if time permits. I think I will stop here, and then if I can answer some questions, and I can give you some answers. I think can we design a generalized efficient adder and use it for any case? No, no, no. Any case is not the case. You have to be very specific about what case you're doing. Say you're designing a generalized adder, but the adder has got a high latency. Then you cannot use that. You cannot use that adder, say for real-time applications. So that's the reason I'm trying to tell you that don't generalize it. So first of all, pick up an application and then do a back engineering and try to find out what type of adder you require, and then start from the adder and try to fit your adder onto that overall big picture. So that is what I wanted to just say. Right. If you have any further questions, please feel free to ask me through chat box or otherwise, and I will try to answer those questions.
Hello. Thank you, sir.
So Vadim has asked me, are there any softwares to conduct device level research? Yes, there are large number. They are not known as softwares. They are known as TCADs, technology CAD. And for example, Synopsys is one of them. We have also Atlas and Athena from Silvaco, right? And then you also have Simica, right? And so there are a few TCADs, but Synopsys happens to be one of the standard TCADs which are available in the market. They're very well defined, benchmarked also.
I think it is done, sir.
Okay, thank you. Thanks a lot. Thank you for giving me an opportunity to discuss with you all of my work. And if there are any questions, just drop me a mail. I will be available. So what are the EDA tools and circuit level for AI chips? Okay, for circuit level EDA tools we are using is Cadence. Cadence happens to be the standard tool we still use it for circuit simulation. You can also use S.P.I.T when you are working with circuit level applications. But even for AIs, we use Cadence. Cadence gives you very well designed, so you don't have to worry about it. So what are the techniques to reduce subthreshold leakage current? Okay, there are many techniques to reduce subthreshold leakage current. One of the techniques people use to reduce subthreshold leakage current is to make the best one you want to know. There is nothing like best one, but people tend to follow two things. One is make the oxide layer slightly thicker. So once you make the oxide layer thicker, you tend to reduce your leakage currents drastically, subthreshold leakage current. The second thing is when many people use it is using this pockets, FDPs. FDPs means I think they are known as I am not forgetting the name. They're dope pockets. So what you do a Gaussian doping and then try to make the Gaussian doping move very close to the drain side. So whenever you change the drain voltage large, it does not affect the source terminal because you have a Gaussian doping and depletion region being generated, and thus you can reduce the suppression pressure. So, is there any further questions? So, thank you very much. Thanks a lot to all of you.
Thank you, sir. Thank you.
Thank you, Dr. Rathod, for your wonderful host. And this is very good. This e-certificate.
Thank you, sir.
Thank you.
This is what we can do. Nothing else now. Everything is E now.
No. This is the new normal now.
It is. I don't know how to say thanks to you, but then I know you was very today. You had a busy meeting. Ministry's meeting was there, and still you have not skipped the session. In morning also you tried to manage for 1 hour, then you went for meeting, and then you completed the given assignment, your promise, and that is very much thanks, sir. Otherwise, people will simply say that okay, I cancel the.
So, commitment is a commitment. And I love actually to interact. I love to
Yes.
interact also.
Yeah.
Because I love to interact with people, and I also learn when I give such talks from the questions people ask. I also learn, so it is useful for me as well. So,
And just for the participants' knowledge, sir is also having online NPTEL courses. Sir is the resource person for this. Yeah. So same courses, no sir? Digital design courses.
I have 3 courses actually currently. One will be running in January. One is currently running in CMOS Digital VLSI Design.
Okay. So, sir, thank you very much.
Thank you very much. All the best. All the best for
Yeah, thank you, sir.
And all of you stay safe.
Thank you, sir. Thank you very much. So, participants, we will proceed with the another session. It's about the Vivado. Are you there, Kumar? Kumar,
Yes,
sir,
sir.
are you there?
Yes, sir.
Manisha, madam, are you there?
Yes, sir. Yes, sir.
Okay. So who wants this thing? Sneha madam, you will share the screen. Screen share. Shall I keep this? Where is Sneha madam? Please disappear from here.
Sir, I am here. I am sharing. Yes, sir.
तुमचं नाव दिसत नाही मला.
सर पण मी आहे सर.
अरे.
पण नाव दिसतले मॅम एस वाले आईस नाही कोणी.
Oh, sorry.
Sir.
It is shifted to top.
Top, present.
Yeah.
Sir. I will just share. Yes, sir.
Manisha madam.
Yes, sir.
So participants, don't worry. It will be a kind of Kumar sir. It's a demonstration kind of session. And ma'am, you please go ahead. Manisha ma'am.
Yes, sir. Yes. Sir, I am trying for the virtual background.
Welcome, sir. Kumar sir, welcome back.
Thank you, Sneha ma'am.
It's okay. It's not allowing me to virtual background. It's okay, sir. I start. So, good evening, everyone. This is our today's session speaker, Mr. Kumar Khandagle, sir. He is the assistant manager at the Edelweiss Securities Limited. He is FPGA developer and front-end VLSI trainer with 4+ years of experience in designing, debugging, and the testing FPGA-based digital systems and embedded systems with SoC. Proficient at the writing Verilog design sources, Verilog test bench sources, VHDL sources, system Verilog sources, C-based application projects for SoC, designed and verified FPGA system with Verilog and VHDL sources on RTX 7, Spartan 6, Zinc 7000, and the Spartan 3 and families. So he possesses the excellent communication skills and ready to work in a challenging environment. So welcome, sir.
Thank you, Manisha ma'am.
Thank you, sir.
Rathod sir, I couldn't able to share my screen.
Just a minute. I
Yeah.
will share.
Yes.
Kumar sir,
Yes, sir.
I just want to give you a small brief. Uh, People, and they have taken their this thing, entire syntax for the Verilog. Okay,
Correct.
but
Yes.
they
Hmm.
show kind of a synthesis and all that, because they would like
Yes.
to
Yes.
see the
Yes.
synthesis in the
Hmm.
reports and all that
Hmm.
demonstration, because I think they are busy from morning 10 o'clock continuously. So you can proceed directly to the demonstrations and up to 1.5 hour up to 7 o'clock, and then it's okay. But you can take a break also. You can ask them if they want a break, or if you want a break any point of time, we can take a break. No issues. It is
Okay.
floors is yours, and for floors is yours and the participants. Now it is up to them and up to you. Welcome, sir.
Yeah.
Okay,
Yeah.
please.
Thank you. Thank you so much, Rathod sir. Yeah. So my screen is visible, right, Rathod sir?
Uh, yes, yes. Uh,
Yeah. It is
yeah,
visible,
it
right?
has. Yeah, yeah, it
Yes.
has come. Correct, correct. Go ahead.
Yeah. So what I'll be discussing is it will not be difficult since we are meeting at very bad time actually, probably a last session. It is not a morning session, so it will be difficult for all of us to actually keep a track. So what I'll be trying to do is we'll be discussing some of the Verilog construct. You already have a good idea of a Verilog construct, but then when we talk about an hardware description language or HDL, and when we compare that with the software, in a software the processor is handling everything, so compiler try to convert your entire C or C++ base code to something that your processor will surely understand, so compiler are strongly designed. But then when we talked about an hardware description language, whatever you write will basically be converted finally to an hardware. So it is very good practice that you keep your HDL synthesizable. Okay, so even though you have a entire idea of all the construct that present in a Verilog, but then that doesn't mean that you able to create a good design. So for a good design, along with having the knowledge of an entire syntax, you also should have some prior experience, and that experience lead us to something called as an Verilog coding styles. Okay, so what I'll be doing is I'll be discussing for some of the time what are the good coding style, and that comes when you have a good experience or you start working on a system. So that things I'll discuss, and then probably some of the hidden treasures that we have in Vivado. So predominantly the tool that I'll be using is Vivado. It will not be a discussion like session. We'll simply have some construct and then we'll directly go for a demo, right? So if you remember the flow for any FPGA based design, we start with a design entry. So design entry basically means that
Kumar sir. Kumar
yeah,
sir.
yeah, yeah,
Full screen. Full screen. Full screen. F5.
yeah, F, yeah, okay. Yeah. So what design entry means is suppose you have a design specification. So the system that you are implementing, right? So you can either start with a Verilog code, you can either start with a VHDL code, you can either start with an C++ code, or you can either start with an Vivado IP integrator, right? So these all are the design entry methods. So usually what you do is from the Verilog that you learn, you infer a system. So for example, if you are designing a flip-flop, what you do is you follow this second technique that we call as an inference. So this is what you believe to be a flip flop, so that does necessarily doesn't mean that it will have a primitives that has been created inside an FPGA to be a D flip flop. There are different versions of a D flip flop, so choosing a correct flip flop will make your design efficient and synthesizable on FPGA. Okay, so bad code can be written in any language. So it is also a case with a Verilog that even though you know everything, bad code can always be written, right? So we start with the very first design entry method. So instantiation. Okay, so what that means is, and for this kind of methodology, when you try to implement a system with this method, the good start is always a library guide. So, for example, if you are targeting an Arctic 7 FPGA family, you look for an Arctic 7 library guide. And if you are targeting for any other family like Zinc family or an Ultrascale family, you look for the specific FPGA family library guide. Okay, so whenever you are targeting this method, okay, the best way to start with is a library guide. Okay, so usually where are the scenarios where you will use this method, that is instantiation method, is if you want to implement a specific size component. So for example, if you are targeting to implement RAM, if you are targeting to implement ROM, if you are targeting on a specific size multipliers adder or a multiplier accumulator, adder accumulator, FIFOs, or a counter, loadable counter, we usually want, what you will probably do is, if you are targeting on a memory, you will try to implement your own memories. So for example, if you can use an if construct and implement your own 1D array, that can serve as a memory. But in this scenario, what happen is it add an extra logic. So this doesn't make your design good fit to FPGA, or in fact, if we can say, it adds some extra resources than what is necessary. And along with that, when we add an extra resources, this basically means that you also add a specific amount of clock delays. Okay, so let us assume that now I want to follow this method. That is, I know that this is the size of a RAM I am targeting. Like, so for example, let us consider that I am targeting to implement 18 KB of memory. Okay, now I am least concerned about whether it can be implemented with a VRAM or block RAM or a distributed RAM. But I know that the RAM is the component that I require. So the family that I'm targeting is an RTX 7. So I immediately Google for an RTX 7 library guide. Okay, so here if you can just go, you'll be finding an entire detail about and various thing, or a detailed description of everything. But this stuff doesn't matter when we are actually designing a system. We directly go to, let us suppose, simple dual port RAM. So the difference between dual port RAM and a single port RAM is you can simultaneously read and write, right? So this is clear to everyone, right? So let us suppose that I'm trying to implement this thing. Okay, so simple dual port RAM. So what I can do is, without just looking into a port, so the port that have been useful for us is D out, which is the data out for me, D in, where I'll be feeding a data in, and then address pins, right? And the write enable. Rest of the pins I can be simply ignored. So let us just go to the template. So this is the template. Okay, so without looking into much detail what we want to see or what all different features that are IP around, what we usually do is, now I have a design specification, that is 36 KB of RAM. So I recognize that I want a dual port RAM. So I immediately go to RTX 7 library guide. There I have looked for a dual port RAM. And inside a dual port RAM, you'll be finding both VHDL as well as a Verilog templates are given. So you can choose any template, it doesn't matter actually. So Verilog template. Now I know that the size that I'm targeting is 18 KB. This is the size that I'm targeting, right? And the width is configurable, right? So let us assume that we want to implement 8 bit of data. Okay, so this is the weight. So width is 8 bit. The size is 18 KB. Okay, so this row, and then the depth you can decide. So let us assume that this is the depth is fine for our application. So this also give us an idea that what should be your read and write address width, right? And then write enable width. So I just gone through a simple declaration or simple initial overview of the micro, and then I just copy this entire thing, right? So I'll just copy this entire thing. Okay, so I've just copied this entire thing. Now I go to an Vivado. So this Vivado ID is familiar to some of you, I guess. Okay, and then probably if I can just delete this thing. So just to give you a clearer picture, I just paste the template that I've been copied from the library guide. Okay, so now this have some predefined structures like 18 KB of size, it is fitted to 7 series, and then rest of the stuff which is mandatory to utilize that micro, right? And then I again go to library guide, and if I can just roll down, I'll be finding some more ports that are mandatory. Okay, so this is how you basically initialize your port to the micro port. Okay, so again go back here, and then we'll be finding now we have the port mapping, which can be used to connect your port to the port that your micro can understand. Okay, so I know that the D, that is the data I'll be feeding into the micro or a RAM, will be 8-bit, and the data that I'll be reading out of a RAM is also 8-bit. So 7 down to 0, 7 down to 0, and then the address. So where I figure out the address. So how you figure out an address? You basically go to the initial comments that have been written. So here, if you figure out, so 8 bit belong to this two rows, and 18 KB, for 18 KB to have a depth of 2048, you need an 11 bit, right? So 11 bit is basically 10 down to 0, and then the two port which will be used to read and write a data will be clock, which will be a synchronizing signal, and the write enable, right? So how you map basically? So DO is basically an output read data port, and for DO we have utilized D out, right? So you simply add D out. For D in, which is a data input, for us it is D in. Read and write address. So for an address we used a common pin, that is address. Okay, so we'll simply add address over here. Okay, similarly for write address also we will feed an address, and then reset pin we do not have, write enable we have, so we'll just replace it with write enable, and rest all things. So this is an RD clock. Okay, so for us we have a single clock port, so we'll just add a clock for both read and write, right? And then we can simply remove rest of the stuff. Okay, so write enable we have already added, and then this thing. Okay, now if you just save your design, you'll be finding, and if I can just set this as a top module, and if I perform RTL analysis where I can see actually an RTL schematic, so you able to see the design that has been initiated. Okay, so this is the first way you feed a design. So instead of writing a Vivado code, now you have utilized a micro. Now the next question comes is when you will start with a micro. Okay, when you use a micro. Now in fact there are two types of micros. Micros are basically a subset of a primitives. So you have a primitives which are the basic or lower level components. So for example, what you considered as a lower level component, something as a flip flop. And when you go one level up, you have a micro. So RAM basically will have a series of flip flop and other clocking management resources, and then you finally get a micro. So micro basically stand at an abstract level which consists of a primitives. So primitives and micros are the most efficient way to implement certain resources on your FPGA. So whenever you are in a situation where you are figuring out the distributed RAM or the block RAM that you have implemented doesn't match to the resources that you are targeting, or it is basically consuming over resources, and you want to find out the most efficient way of utilizing the resources on an FPGA, you start with either micros or a primitive. So this is the scenario where you will be choosing micro and primitives. So only when you figure out that the coding that you are using, that is an inference coding, okay, or the coding that style that you know, and you are targeting an implementation of a RAM or a memory, but you are figuring out that it is not matching to the resources that you are targeting, or it is consuming some over resources. In that scenario, you always prefer to go with a macro or a primitives. Okay, and if you can just see an RTL schematic, you'll be finding an exact micro has been initialized. Now it is very difficult to actually initialize a micro by an inference coding. So if you write a code, we'll shortly see when we write our own code to implement a RAM, it doesn't always infer the efficient BRAM micros. It can infer anything. It can infer BRAM, it can infer distributed RAM, and so on and so forth. Or in fact, it can use a different flip-flops combination to implement a RAM. But this is the most efficient way by which you can implement a RAM. Okay, so this is the first scenario where you will be choosing to use a micro or a primitives. So when you have a scenario where you want to most efficient utilization of resources, you either proceed with a micro or you proceed with the primitives. Okay, similar to micros, primitives also will be utilized in the same way. So for example, you have a instantiation template for a D flip-flop. You just need to replace the ports with the your ports. Okay, I guess this thing is clear, right? Yeah. So next thing, what you can do is if this method is not what you are looking for. So this is one of the method by which you will be implementing the component. But let us assume that you are not targeting this component. So you are not targeting RAM, ROM, multipliers, adder.
Hello.
Yeah. Yeah.
Yeah, these
Yes.
macros are similar to IPs.
Uh, mm, yeah, you can say that, but then IPs are further higher level as compared to micro. So you'll be finding a combination of micro are sometimes called as an IP. But usually Vivado separate them. So they have a separate class called as an IP and they have a separate class called as an micro.
Okay.
Yeah.
If you infer those, is it possible to test those for the, required specifications in the sense that whether it is functionally working or not, with what delays are there? Is it possible for us to test it using test bench?
Yes, 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 it is possible. It is
Oh,
very possible.
okay. Okay.
So yeah, so what I'll request you is it will be good that you if you can interact in between. It is not at all a problem with me, right? So if
Okay.
you find any problem, you can interact at any time, right? Yeah. So if you have a requirement of implementing this component, so if you have a good design specification and you have understood that this is the component that you are targeting, then you always go for a micro. This will consume the least resources that is possible with any design, right? Or you can go with the primitives, but primitives are a bit dependable. Okay, so you can write a very good Verilog code and you can actually infer a primitives in an easy way. So inference can lead to primitives very easily, but inference technique leading to a micro is bit difficult. Okay, so primitives can be safely ignored. So whenever you find out that where we actually use a primitive, so this might be a question. So let us assume that you want to have all we'll just see an example. Okay, so that will be a good idea actually. So when we looked at a second technique, you will have a good understanding what I mean. Okay, so second technique is an inference. So whatever you have learned about an Verilog so far, okay, so the morning session that you have did is basically building your inference skill. So inference is how you look your system. So for example, you are implementing a flip flop, so it is purely your inference how you are looking at an flip flop, and then how you are utilizing a Verilog construct to implement that flip flop. So that kind of a coding is a second way by which you can feed a design entry to an Vivado. In fact, in any FPGA based design flow, that is the second way. Okay, so instantiation basically will differ only in an primitives or a library. So if you are targeting on an Altera Cortex or Intel Cortex, you'll be finding that they have a different primitives or a different micro, but the rest of the design entry method remains same. Similarly, if you're targeting a Xilinx family, so you only have a differences in a micros and a primitives, but the method will remain same. So this will be the first method. Second method is an inference. So inference is whatever you learn about and very long. Now nobody can be a perfect, and there can be debatable questions on what should be a good coding style and what should be a bad coding style. But then what we do is we generally follow certain set of rules. So that rules comes from an actual device that have been finally converted to an ASIC chips. So usually Synopsys provide a good design rule, and in fact Vivado itself provide a good design styles. Okay, so that all is considered as an good coding guidelines. Okay, so whenever you look for an inference technique, we usually look for an good coding style. Okay, so what we'll do is we'll look at an example one by one, and we'll try to understand what are the good coding styles. So this probably all this stuff you already have discussed with and very long. You have discussed if else statement, case statement, how you implement a memories, how you implement an FSM, then assignment operators, probably continuous and procedural assignment, and inside a procedural assignment you further have blocking and non-blocking. You also have a different modeling styles and the type of project. Okay, so for each of this construct or a technique, you have a certain coding guidelines. Now what coding guidelines will do is it will basically it will convert whatever you are looking for or what your specification are into exactly what FPJ can understand. Now this becomes a bit difficult. Now let us try to understand and with an example. Okay, so for each of this case, we'll consider one example. So probably you'll have a good idea what I'm trying to say. Okay, so the most simplest effects. Okay, so whenever you are using an if statement, always add an else statement. Do not just ignore an else statement, otherwise it may lead to some serious consequences. So for example, let us just go back to our sources, and then here you have this example. Okay, so what I'm trying to infer is I'm trying to implement a flip flop. Okay, so my agenda is basically to implement a simple D flip flop. So it basically follows a data D. So flip flop have a D out, which is an output pin, a clock pin, which will be used as a synchronizing input, and then the D in. So our flip flop will basically follow D, right? So this might be a very simple representation of a flip flop. So what I'm doing is always at a positive of a clock, I am simply copying the content of D in into a temp. And since this is a procedural assignment, so it doesn't directly allow us to add a D out. So I can in fact add a reg over here, and then I can use a D out. But instead of that, I have used a reg temp. Okay. So now let us just make it as a top module and see what Vivado infer out of. Okay. So I'll just reload my design. Yeah. Cool. Viraj, can you mute yourself, please? Viraj? Hello, Viraj?
अभी यहाँ का खत्म हो गया क्या वो साइड पे का काम
Viraj, can you please mute yourself?
आप
Rathod
नहीं
sir?
करोगे
Hello.
अच्छा
Sneha ma'am? Hello. Hello.
हा सर राठोड सर होस्ट आहेत ना त्यांनाच होईल ते म्यूट करायला.
Rathod sir?
हा सर बोला.
Virajला mute करा please.
त्याला काय झालं, पण काही इश्यू आहे? नाही, ते सुद्धा मूट करू शकतात. एक मिनिट.
Virajचा
अच्छा
I
अच्छा
guess
अच्छा
background noise.
अच्छा ओके 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 ओके. हा ओके.
Yeah, thank you. Okay. So these are the port, right? So we have a clock, D in, clear, and D out, right? So what I've done here is always at a positive of a clock. So I'm making my flip flop sensitive to a positive edge of a clock, and then the output will simply be following D, right? And I've saved my design, and now I am opening my schematic. Okay, let us see what Vivado infer out of it, right? So we haven't utilized clear yet. We'll try to utilize that also. Okay. Okay, so here if you just go to a schematic, you'll be finding, since we haven't utilized clear yet, so it have inferred that it is an RTL reg. So the primitives that we have inside an RTL, so it is an RTL register, and it is a D flip flop. So we have a D input, so D in and clock, and we have an output. Okay, so everything looks fine. So not at all bad. So the code that I've written looks fine right now. Let us just move ahead and now add something for a clear. So what I'm trying to do is clear will be an active high. So as soon as clear is high, I'll not do anything. As soon as clear is low, okay, clear is low, will basically follow an input. So if not of clear, okay, so if not of clear, then we'll basically, because since it is an active high, so as soon as clear is high, we won't be doing anything. But if clear is 0, we'll be simply following an input. So this basically act as an asynchronous input in our case. Okay, so let us just save our design. So here I have forget to add an else statement, right? So remember this point that I have not added an else statement. I thought that it should be automatically inferred by an ID. Let us see if I can just reload my design, and if I can see some changes in my schematic. Okay, so I want that this should be connected to an asynchronous or basically a synchronous reset pin of a flip flop. So you'll be finding the component that Vivado is using remains same, right? It is the same T flip-flop, but it started to use a clock enable pin now, and then it have added an extra RTL mux, okay, which we don't mean. What we meant is it should be connected to, from a coding itself, you can guess it should be connected to a synchronous reset, right? So this is what we meant, but then the inference that software is doing out of this pin is it have added some RTL mux and that it is connecting to a clock enable. So this is not what we want, right? Everybody can agree on this point. This is not what we want. Now if I can just add else statement, okay, else temp equals to 0, okay, and in fact good coding style will be to add 1-p to a 0. And now if I can just reload my design, and if I now go to a schematic, let it just refresh our schematic a bit, okay. So what we did is, okay, so if clear, and then so this should be 0, else it should follow D, right? And now if I can just save my design and if I can reload a design, so we'll be finding now just adding an if statement and adding if and else in a right way leads to shortening of a component, right? So initially when we tried twice, we able to add an extra mux along with this, and it has been connected to clock enable, which we don't mean, right? We went to connect it to either synchronous reset or a synchronous set. So when we write a good course like this, so if you don't forget to add an else statement, it won't infer an extra logic. And in most of the worst scenario, what happen is when you are working on a higher clock frequency like 100 megahertz, this is very simple design, so it won't lead to a creation of a latches. But then when you are targeting on a higher clock frequency and a complex design, in that scenario, if you forget to add this else statement, if you forget to add the else statement, it leads to a creation of a latches, which further restrict your maximum clocking frequency. Okay, so this is the first coding guideline, that whenever you utilize a if, you always add a else statement. Okay, so this thing is clear to everyone? Yeah. Okay, so this is the first coding style, that is whenever you have a if, you always add a else statement. Do not allow the software to infer what you are targeting, right? So if you make your code complete, the design will be smooth, and in fact it will be the shortest consume it will consume the shortest resources on an FPGA, and it will be perfect. Now as soon as you make a perfect code, you'll be finding it able to infer the perfect component what we are targeting. Okay, so let us proceed further. Okay, so next is a very popular and very useful is a case statement. An extension of a if is an case statement. Now usually we as a new coder, or whenever we entered after learning a Verilog from a different sources, we always forget to add a default case. Now this leads to an inference of a latch. Now adding a latch is not always a good choice when you are targeting something on an FPGA. FPGA are very bad at handling a latches, and in fact it further restrict your frequency requirement. Okay, so whenever you have a case statement, you always see that you add and default statement. So let us see an example. So with an example it will be a bit clear. Okay, so here is an example. So I'll first set it at the top. Okay, and then let us just look at a code. Okay, so if you looked at a code, so it is basically a simple multiplexer. Okay, so multiplexer consists of in our case it consists of three 8-bit inputs. Select line, since there are three input variables, so we required a bus size of select line to be at least 2-bit, right? So for that reason I have chosen it to be 1 down to 0. And then this is a Verilog 2001 style, so instead of declaring different uh, reg variable for an output, I have utilized a reg in the output position itself, right? This thing is clear. Okay, so what I've did is, since this is a combinational circuit, Okay, so first thing is, now I have identified that it is a combinational circuit. So if I proceed with a procedural assignment like the always statement, so I'll stick to a blocking assignment, right? So for that reason, I have utilized this equal sign. Okay, if this could have been a sequential circuit, then I need to follow a non-blocking style, right? So we'll look further what blocking and non-blocking coding guidelines are, but then this is pretty much clear, and this has been added in Verilog 2001. So before Verilog 2001, we used to add a in or b in or c, or a in comma b in comma c. So all the three methods are fine, but now we shifted to use this method, and in fact Verilog highly recommend to go with this method. So asterisk sign indicate that our entire process is, or entire always statement is sensitive to all the inputs that we have in a design. So as soon as any one of the input changes, our output will be evaluated, right? And output is d out. Okay, so you'll be finding that here, now since I only have a three cases, so 0 0, you will be connecting d out to a in, right? 0 1, you'll be connecting d out to b in, and in 1 0 and d out to c. So this is it, because we do not have any other input uh, other than A, B, and C. So I'll not add anything. This basically means that when I learn and Verilog, this basically completes my entire code, right? So I'll just see you my design. So what I'm inferring out of it is Verilog should consider this to be 4:1 mux. This is what is my inference out of this code. Okay, so I'll just reload my design and let's see what Vivado infer out of it. And this in fact is not valid for Vivado. Even though you are using an Altera or an Intel FPGA, then also it is fine. Okay, so this coding guidelines is valid for everything. So you'll be finding now something is a bit wrong. So what is happening is, so it able to infer 4:1 mux, but then it is using two 4:1 mux, and in fact it have also added a latch, which is very bad example of a bad code, right? So whenever we have a latch inside our RTL schematic, this means that we have made some big mistake in our code. So this is what happened when you write an incomplete case statement. So whenever you have an incomplete case statement or incomplete if statement, you basically infer a latches out of it. And this is a good example where you have actually infer a latch statement. Okay, so how you clear this latch? Very simple. So I'll just go to my code. Okay, if I just go to my code, and the good thing with Verilog is it support a multi-block command, which is not available in a Verilog. So it follows a block level commenting similar to a C. So that is good point. And then now let us just use this code that I have written over here. Okay, so here only one modification I have did. What I've did is the default statement is D out should be tied to an E. So this is the only one line that I have added to our previous code, and this is our previous schematic. Now let us see what will happen by just adding a symbol line. Okay, so let us just go in here and let us just save our design. Okay, so when you save our design, Vivado will automatically understand that you have made some changes, so you simply click on and reload. And in fact, it's always a good idea that you remember some of the TCL command in this case, because going again and again back to the RTL schematic and then performing an elaboration. Instead, you can remember this command also. So you can just go to a TCL console and then you can just type update synthesis, and then you can simply add an RTL. So that will automatically basically allow an automatic elaboration of the schematic. So let us just go to a schematic. Now we'll be finding this is what we are expecting, right? A single 4:1 mux and without a latch. So this signifies that we have made everything correct, right? So up to this point, whether everything is clear? Yeah. So whenever you have a case statement, never forget to add a default statement, right? Either it will lead to a creation of a latch. So these are two good practices that we always follow. Next thing is blocking and non-blocking. In fact, most of the Verilog coder, we also don't know how much we know about blocking and non-blocking. So they are the most mysterious assignment operators that we have inside a Verilog. And in fact, nobody can say that I know everything about everything about blocking and non-blocking assignment. Okay, but these are some of the safe guidelines that have been given by Synopsys. So these are the guidelines given by Synopsys. So whenever you have a combinational circuit, remember, whenever you have a combinational circuit and you are sticking to a procedural assignment. Okay, so there are two types of assignment that we have inside an Verilog. One is a continuous assignment and second one is a procedural assignment. So procedural assignment is basically we are waiting for certain event to happen and then only we evaluate, right? And in a continuous assignment, we do not wait for an event. As soon as we have an RHS, we basically evaluate LHS. That's it. Okay, so we are sticking to a procedural assignment, that is we are using an always block, then always stick with a blocking assignment. Okay, and in fact, if you remember our example, so 4:1 mux is a combinational circuit, right? So this is my first inference that it is a combinational circuit. So, and still I am targeting to go with a procedural assignment. Since you'll be finding if it is 2:1 mux, I would have preferred to go with a continuous assignment, right? Because we have a ternary operator where I can easily evaluate 2:1 mux. And then if I target a structural modeling style, then I can go with a 4:1 mux. But then in that scenario, our code will be quite big. So procedural assignment is quite small in this case, right? So I choose to go with basically uh, procedural assignment. So always, right, always I have used that signifies I am targeting on a procedural assignment. So in this case, whenever I want to connect an output or I want to evaluate an output, I always use a blocking assignment. So here you'll be finding I have utilized a blocking assignment. Okay, now you'll be finding or you can see if I use non-blocking assignment, right? So if I use non-blocking assignment, let us suppose, okay, and if I save a design, let us see what happens. Okay, you could say that this is also fine, this doesn't create much problem. Okay, so let us see what happened when we replace that with a non-blocking design. Okay, and if we go to schematic over, this look exactly similar, right? So everybody can see this is exactly similar to what we are getting with a blocking assignment. So then where is the problem? Why the synopsis is suddenly telling that whenever you have a combinational circuit and you are using a procedural block, you go with a block? The problem is you'll be finding the problem when you actually perform a simulation. So when you use blocking or interchangeably, if you used by mistakenly, if you have utilized a non-blocking assignment instead of a blocking, it won't change much to the component that have been created, and that you can see over here also, it have not changed much, right? Or it is exactly same. But when you perform a simulation, their problems start arising. Okay, so let us just see an example. Examples are always a good idea. So instead of writing a test bench code over here, I have utilized a simple lightweight EDA playground. Probably everybody is familiar, right? So now here is a simple 2:1 mux, right? We'll be finding input A and B. Okay, these are the two input for our mux. Then we have a select line, we have a reg, or that we declare as a Y, since we want to use this inside a procedure block, right? So always at asterisk, this signifies that our circuit is a combinational circuit. Begin. If select is 0, y is tied to an A, else y is tied to a B. So you'll be finding we are following an asterisk Verilog 2001 guidelines. So that is perfect. Along with this, we have also included else statement. So if and else, so this won't create any problematic scenarios while implementation. Okay, so this code looks perfect. And then we have written this test bench. Okay, so here I have basically used this code, and then I have created an instance Steven for it, right? And then all the inputs, so if you have an experience with the test bench, so all the inputs we declared with a rec. Okay, so for that region, input A and B are declared as a reg. In fact, select is also an input, so select is declared as a reg, and whatever output we have, we basically declared them as an wire. Okay, so this is what we do when we write a test bench. And then you create an instance, you basically connect this variable to the variable that you are testing, right? So this is what I have done. And now I have written something, right? A equals to 1. So I want to force this to a 1, B to 1, and select to 0. Okay, and then I have utilized the display statement, right? And here what I'm doing is I'm just printing the values of A, B, select, and 1. And now if I just try to run the code, we'll be finding this should basically give us a result as A should be equals to 1, B should be equals to 1, select should be equals to 0, and Y should be equals to A, which is 1. But here you will be finding something which is not what we are expecting. Okay, so value of A is shown as X. It is basically an undefined value or don't care value. We see B is also X, select is also X, and result into Y, which is also X. So you'll be finding this doesn't create a problem, much problem, when you convert the code into a circuit or a primitives or a micros. But then when you go for a simulation, it starts to create a problem. Now if you just go to the reason for what is happening, actually why we are getting an error, so you basically come to a scenario where we need to learn about system verilog events. So what happen is whenever you perform a simulation, simulator basically schedule or divide the different event that you have inside a Verilog code into different categories. So what happened is you have very first code that have been executed. So this all fours are a sub part of the simulation. Okay, so you have a simulation. So this is the code that we are scheduling. Now what Vivado simulator, or in fact not a Vivado simulation, in fact if you have seen, this is an EDA playground, and here we are using Synopsys VCS simulator. Okay, so you choose any of the simulator, but then still you'll be getting the same result. Now this is a universal rule that your code will be divided into 4 parts. Okay, so first part will be an active region. An active region will allow an execution of a display statement, a continuous assignment statement, and a non-blocking assignment and blocking assignment. Okay, so what happen is in the first part your display statement will be executed, continuous assignment will be executed, evaluation of a non-blocking assignment happened in the first region, but it is not assigned to left hand or LHS. Okay, so even though it is evaluated, it is not available for us to see. Okay, so just an evaluation happen over here, and evaluation and assignment of blocking assignment both happens in a first region. Okay, so both happens in a first region. This is the first region. So if we just go to this code, we'll be finding this will be the statement that will be executed first, right? And then we have this non-blocking statements which will be evaluated, but they will not be assigned to A, B, select, or Y. And for that reason you'll be finding even though A we have tied to a 1, but then this will be evaluated. That is, the simulator will know that the next time, next, in fact not a next time, in a next event we know that A should have a value of 1, but at this instant, at the first level of a simulation, we do not know what is the value of A. So for that reason you are getting A as X and B as X, and also select as S. Okay, this is bit difficult to understand, but if you can just follow, you'll be able to understand. Then you have a second event, that is an inactive. Okay, inactive basically means when you have a delay of a 0. So hash 0, when you add, just to add some minimal amount of delay to simulation, for a simulation to happen, you basically mean that as an inactive. Then the third is an assignment of a non-blocking event. So whatever we have evaluated in this case, it will be assigned to its respective LHS side. Okay, so actual value of LHS, of this LHS, will happen in this third part. And then finally you have a monitor and a stroke, which are basically evaluated last. So you'll be finding the simplest solution to see this as a working, simplest solution to this as working is if you add something that happened last. So after all the events are scheduled, the something that happened last will be simply removing an error. So if I can just replace this with a monitor, if we can just replace this with a monitor, and if I can just execute the thing, you'll see suddenly something amazing happens. You'll be able to see 1 1 0 and 1. Okay, and this is what we are expecting, because whenever select is 0, y should be tied to any which is having a value of 1. So why this is happening and why display is not happening, now you can guess clearly. Now if I just add a display over here, you'll be finding suddenly our values are gone. Okay, the reason is the display schedule in the first region of our simulation, but the assignment of the values actually happen in a third region. So for that region we are getting an X. Okay, and with a monitor it actually happened at a last, and this is what consists of a first clock cycle of a simulation. So we'll be finding the this coding style doesn't create much problem if you are pretty much safe, much problem when you are targeting on a synthesis like stuff. So you'll be finding an exact schematic you'll be always getting, either you follow blocking modeling style or blocking assignment or a non-blocking assignment. But with the simulation it is bit tricky. Okay, and now if you have this idea, you'll be finding that it is always a good idea that you use a monitor or a strobe. So independent of what you are targeting, blocking or non-blocking, you'll always see a result. Okay, so this is why whenever you have a blocking assignment, and then if you are targeting a procedural assignment, or in a simple way, if you are targeting a combinational circuit, and if you are targeting a procedural assignment, go for a blocking assignment. Okay, so this won't create a problem with the simulation also. In fact, it won't create much problem with the synthesis, but simulation also will be error free, right? The next thing is whenever you are targeting a sequential circuit. Okay, so wherever you are the fast, you make your entire system sensitive to a single fastest signal, which is a clock. In that case, if you are targeting a procedural block, always prefer to go with a non-blocking assign. Okay, so these are the most safest tool that we have, and never mix the blocking and non-blocking assignment. So this is the most uh, unrecognized error that we sometimes make. So when you are writing a big FSM, sometime it may happen that the non-blocking assignment operator becomes a blocking assignment operator. So you wouldn't able to recognize that in a simulation. So simulation will give us some incorrect result, but you'll be finding the entire code is just perfect. So never mix blocking and non-blocking assignment. So if there is a scenario where you won't able to decide which assignment to use, always go with a non-blocking assignment. So these are the most safest tool that we have. Combinational circuit, directly go with the blocking. Sequential circuit, go with the non-blocking. You don't know which assignment to use, prefer to go with non-blocking. Yeah, yeah, anybody have a
Yeah.
question? Yeah.
Yeah, generally the combinational circuits, do they require this process to be written like always? Because in VHDL for the combinational circuits, we can write in AND gate Y, I mean, is equal to, I mean, the variable then differently, and if it is a signal, then arrow and equal to A and B. So there is no process involved as such. But here, do you recommend that we have to write a process for the combinational circuit equations like Boolean equations?
Yeah. So this question actually can be understood in much greater detail when we target modeling style. Since uh, because because what you are looking at is a gate level or a data flow modeling style, right? So that is different scenario when you choose a data flow modeling style. But let us assume that now, without having much understanding of a data flow modeling style, you are just sticking to a concept that I'll either prefer a procedural assignment or a continuous assignment. So for a continuous assignment also, and there are multiple ways. In fact, a single system can be implemented with a 4 different types. So you can go with any modeling style, right? So data flow will also result into same component, behavioral will also result into same component, so on and so forth. The only difference is you'll be finding you have to write more number of lines, right? uh,
Okay.
yeah, only that is the difference, that you have to write a more number of lines as compared to what you are targeting. So it won't create a difference at all, even though you prefer to go with the gate level modeling style, structural modeling style, a behavioral modeling style, or a mixed level modeling style. It won't create a different component or a primitive. Only difference is it will increase the number of lines of code that you are writing. That is the only difference that I have figured.
Okay, I think from this I conclude that if at all you have to write the combinational logic using process, then
Yeah,
it should be the blocking statements. The statement
perfect,
should be of
perfect,
blocking type. Is that
perfect.
okay?
Yeah, that is perfect.
Okay, okay.
Yeah. Next thing is FSM. Now these are very very common. So any project you'll be finding you'll always have an FSM, right? So everybody will agree with on this. So whenever you are targeting a big project, you'll be finding at least one or two FSM will always be there. And FSM are always misunderstood until and unless we have a certain, and we'll be finding there is no certain methodology to write an FSM. We blindly start, we blindly understand a state diagram, and we blindly actually write an FSM. But there do exist a methodology. So this methodology is has been given by Vivado. It has not been given by Synopsys, but these are the most perfect way of writing an FSM. So you won't be finding any perfect way or any efficient way of writing an FSM. So anybody have heard of this methodology? Anybody have idea about this methodology? Probably you have some experience with an FSM. Okay, okay, fine. So what one process methodology is, or in fact, if we consider an FSM, there are three ways in which we actually can write an FSM. So I name them as, in fact, this is the naming convention that I have given. It is a three process methodology, it is two process methodology, or either you can go with an one process methodology. So let us just see with an example what that means. Okay, so here I have one code, so very simple code. Okay, what I am doing here is I have a clock which is a synchronizing input for us, a reset pin, okay, D in and then D out. Okay, in fact I have included a D in, but I am not implementing a relay machine, so I can simply remove this thing. So I am basically generating a mood machine. Okay, so mood machine is something where your output depends only on the previous state, it doesn't depend on an input. So I safely removed a D in. But just to generalize, since Mealy can be considered as much abstract way of representing Boolean machines also, so I have included a deal. So you have a generalized idea. If you jump into a situation of implementing an FSM, this is what you need to do. Okay, so all, and since this is a methodology, we usually do not infer much of the logic out of it, but this is how you should write an FSM. Okay, so create two state, always create two state. One is the state and another is the next state. Okay, so state and next state. So always when you are writing an FSM, you create a two state, then you declared all the state that you have in an FSM. Okay, so FSM will have a finite number of states. So in our case, I have assumed that it only have a two state, so S0 and S1. Okay, and I have utilized the parameter, okay, construct of an Verilog. So S0 will be having a value of 0 and S1 will have a value of 1. Okay, so this is perfectly okay. And do not just remove this thing. Okay, so if we just write like this, this is infer as an integer in an Vivado. So this probably you have an idea, since you already have a session on an Verilog, you'll be finding you write something like this is inferred as an integer. But I know that I only have a two state, so two states can have a value either of a 0 and 1. So it is always a good idea that you specify the size of the variable that you are specifying. So one basically signifies that I am signifying a single bit which will be having a base of binary and it will have a value of 0, right? So three process methodology means we will be dividing our FSM into three subsystems. Okay, one will be this process, two will be this process, and three will be this process. Okay, so in fact it is Verilog or VHDL, it doesn't matter, you can follow the same methodology. In an VHDL you have a process instead of an always, and then you have a sensitivity list. You do not have this at the rate operator. The only difference is only the always has been replaced with a process, and then you do not have an at the rate attribute, right? And then you also have a sensitivity list. So rest of the things remain same. So first thing is, whenever you are targeting a three process methodology, and in fact this is the most simplest way of starting to write an FSM. So whenever you are in a situation where you want to write an FSM, you start with the three process methodology, right? So three process methodology mean we will be having the three always, okay, or we'll be doing three different processes in a three different always, right? So first always, second always, and third always. Okay, so first always, remember first always, where we'll be sensing a reset pin, should be sequential or a non-blocking. Remember this thing, the first process where we'll be sensing a reset pin, should be sequential or a non-blocking. So sequential means that our always will be sensitive to a passage of a clock, right? If it would have been a VHDL, it will be process clock, and if rising edge of a clock, only that is the difference, begin. So if reset is active high, assume that our reset is active high, So if reset, so this basically is if reset is 1v1. Okay, only that is the difference. So if reset is true, will remain in an state as 0. We will remain in an state as 0. Else our state will be next state. Our state will be next state, whose value we do not know right now because we haven't written anything for a next state. So first process is where you will sense a reset. Okay, so if reset is high, you will remain in one of the reset state, and you can write anything you want. Okay, so whatever you want to do in a reset, you can write over here. So d out can be safely equals to 0, and then if you have certain other inputs or an outputs, you can do certain processing over here. Now you'll be finding it is showing an error because whenever you have a multi statement, we need to add a beginner, right? So this is a convention that we have in an Verilog, right? So you can do anything what you want in a reset state. But just to make the entire FSM very, very simple, what I've did is if reset is true, state should be equal to S, else state should follow next state. And then from where this next state is coming, it will be coming out of certain different process, which will be a next state decoding logic. Okay, so this is the first process, and this is a very simple explanation that I have given. And I think looking at a code, it is not much difficult to understand. Now let us try to target the second process, where we'll be actually sensing what should be the next state value. Okay, and remember, other than the reset process, rest all the process will be combinational process, so they will follow a blocking assignment. Okay, only this thing you need to remember, that first process will be sequential, so you need to follow a non-blocking assignment. Rest process will be combinational, so you need to follow a blocking assignment. Okay, so we'll be finding always at the rate second process where we are sensing what should be the value of next state. So it will be depend on state or d in. Now this is the case when you are implementing a Mealy machine, right, where your next state depends both on an input as well as a previous state. So if this would have been a Bure machine, you will have simply removed this, and then this becomes Moore machine, right? So I'll just keep it state or D, right? Begin. And then you simply perform a case on a state. Okay. Now, why I'm performing case on a state, you'll be having this question, because I know that my clock, as soon as my clock changes, because the only single signal that will be changing inside my system is a clock. So as soon as clock changes, everything should be evaluated. Now we know that as soon as clock changes, the state values are evaluated. So now for rest all the process, we have only two signals that are changing. One is a clock and other is a state. But if we have utilized the clock in the subsequent process, they will become a sequential circuits, and we do not want that. So we only left with a single option, that is state, right? So as soon as clock changes, state changes, and as soon as state changes, we need to evaluate the state. Okay, so case state is okay. So whenever we are in S0, whenever we are in X0, next state is S1, and whenever you are in S1, next state is S0. Now you can write whatever things you want to do. For example, next state you want to perform some different logic, you can add over here, just adding begin and end. Okay, so this completes our second process where we are decoding our next step, right? Third step, the third process is again a combinational process. So if this is a Mealy machine, we have state or D, else it will be simply state, right? Begin, case state is S0, and now whenever we are in S0, D out should be 0. This should be anything, okay, and S1 should be, D out should be equals to 1. Okay, so you'll be finding why I have named this as three process methodology, because whenever we consider an FSM, there are three things we need to evaluate. First is what should happen when we add a reset. Okay, so this is the first thing. For that we have written one process, what should happen to an output, okay, and what should happen to a next state. So when you divide this three different scenarios into three different always block, you basically have a three process methodology. Now from naming itself, you can guess that what should be a two process methodology, right? So it will only have a two process. Now you'll be finding the most easiest way to merge two process will be, because see, these two processes are been sensitive to same input, so I can simply merge them, and if you merge them, then you have something like this. So I'll just comment this, and I'll just highlight the next code that I've written. Okay, so you'll be having a good idea. So, and then I'll just remove this thing. Okay, and now let us analyze the code. Okay, so what we did is this remain as it is in a two process methodology. Now we have a two process. First one is we will understand what should happen with the reset. So this remains as it is. So if reset is high, state should be S0. As long as reset is high, state should be always S0. Else state will follow a next state. Now we need to write a code for a next state. So always at state or DE. Now case state is this remains as it is. Now why we have not written next state over here, because the upper process is sensitive to clock. So on the edge of a clock, state will be evaluated, so state will be changing. So we need to make, as soon as state changes, we need to evaluate our next state, right? So S0 begin, and then as soon as you add a begin and end, you can add a multiple statement inside the various cases that you have in a state, right? So next state should be equals to S1, and then D out should be equals to 1 dash B0. Now you will be finding here I have made one mistake, that is this is a combinational circuit that I am trying to implement or trying to infer, and I have used a mixture of both blocking and non-blocking. So this should not happen. This should be blocking. Okay, since this is a combinational blocking, and then this will be exactly similar to what we are getting out of it. But you'll be finding this three process methodology is quite easier at an initial state as compared to two process methodology, right? Now the most toughest part, and we always implement FSM with following this process methodology only. Okay, we never prefer to go with a one process or two process or three process. We always implement our FSM in this way. Okay, so you'll be finding on the net, if you search for a code related to any FSM, you'll be finding the code is always written in this type. Okay, it won't be that much simple like this two process or three process methodology. So always at a positive of a clock. Now your entire process or your entire circuit becomes sequential. So you'll be finding, even though your output remains same, it will add certain components in between, because initially these two components are been combinational, but now they are become sequential, right? So you'll be finding some extra registers have been added in between, just to follow the coding style. Okay, so let us just look into one process methodology. So positive edge of a clock, if reset state is S0, else begin, and then the entire thing, so case state. Okay, and since this is a sequential circuit, so state should be equals to S1. Whenever we are in S0, we'll move on to S1. Output is 0, operators are non-blocking. S1 we go to S0, and output will be equals to 1. Okay, so this is how you write an FSM. So whenever you are in a scenario where you want to implement an FSM, it is always a good choice that you follow at least two process methodology, at least at an initial stage when you are verifying your design, and later once you verified your design, you can go with this. But in most of the cases, if you are referring to the codes that are available on a web, you'll be finding this kind of methodology is there. But there are three methodologies available for an FSM. So whenever you start designing a system, follow a three process methodology or a two process methodology, and once you finalize your system that it is working what you are expecting, you go with a one process methodology, right? Yeah, so I guess everything is clear up to this point, right? This is a bit heavy. I try to make it as simple as possible. Yeah, next we have is a mod. Yeah, anybody have a question? Yeah.
When you go to two process methodology,
Yeah.
we infer the Mealy machine.
Yeah, so when you have a melee machine, a scenario where you have a melee machine, right? So what you do is you just modify this code a bit so you'll have an understanding. So let us assume that we'll be changing a state only on an input. So for example, this is the state, right? So reset won't affect our input sensing, right? So now reset is 0, so we want to decode a next state. So whenever we are in this state, so here before proceeding to next state, we'll basically do this thing. So if bn is 1, we will basically jump to next state. Else 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 we basically will be staying in this state only. Okay, and then we'll basically add it. So now what we'll be finding is, probably I have forgot to, yeah, Dean is there. So here what I'm doing is, yeah. So what happened is, the difference between Moore machine and Mealy machine is basically, basically when how your output should be evaluated, right? So in a case of a Moore machine, your output depends only on a previous state. So if you consider a previous example, you'll be finding, see, if I just comment this two lines, you'll be finding that as soon as we jump into, let me just, yeah. So as soon as I jump into an S1, you'll be finding my D out becomes 1, right? Or as soon as I am in an S0, my D out becomes 0. So here I'm not sensing what is the value of a D in the input that we have. So it is basically an example of a Moore machine. But now suddenly I want that, instead of depending on a previous state, I also want to depend my system on an input D, that is a present input. Okay, so this basically turns your Moore machine to an Mealy machine. So here what I'm doing, even though I am in an S0, that is my previous state, until and unless my input is 1, my output won't change, right? Whether you able to understand, Shaila ma'am?
Yes, sir. Yes, I understand. Yes.
Yeah, yeah. So let us consider next. So probably time is running very fast actually. Yeah. So modeling style. Okay. So this is the most difficult thing to do when you start a coding. Okay. You have a system specification and nobody knows what is inside the system. So you have something like you implement a interface, an SPI interface for a DAC, or SPI interface for an ADC, or you implement an interface that will basically allow an FPGA to communicate and to a console over an Ethernet. So nobody knows what should be inside a system, right? We cannot infer anything. What are the components that we require to do that? In fact, when we say that I want to implement a simple interface like UART, where I can communicate with the PC, nobody can infer what should be the component that I require. So in that scenario, see, whenever you start with an application where you don't know what is inside a system, so always start with a behavioral modeling style. And in fact, without stating this rule also, you need to follow a behavioral modeling style. You do not have any other way. For a simpler system like a ripple carry adder, you know that it consists of a full adder, or it consists of half adders. Finally it consists of a logic gate. Okay, so in that simple scenarios, you can infer what is inside our system. But whenever you are targeting on a projects, you never know what should be, what must be inside a system. So in that scenario, always start with a behavioral modeling style. So remember this thing, that even though if you don't remember this rule, you need to start with a behavioral modeling style. You do not have any other way. Okay, but for just for an information, if you can infer your system with a basic logic gate. So for example, let us consider a very simple example like half adder. So you know that it consists of a XOR gate and an AND gate, right? So in that scenario, you able to infer your system with a basic logic gate. So there you follow a gate level modeling style, right? Now the question which has been asked previously by Shaila man, that is why we are not using a gate level primitives that we are having in VHDL, instead of using a process and all this. Now for that simple scenario, as soon as like 4 is to 1 mux or 2 is to 1 mux, as soon as you know that you know an equivalent boolean representation or an equal logic implementation of a system, you immediately will go a gate level modeling style, and there will not be any scenario that you will be following a process or a process, right? But for a complicated system where you cannot guess what is inside a system, you need to follow a behavioral modeling style. The next is, if you want to reuse your component. So for example, for a full adder, you know that half adder primitives are not there, but the basic logic gate primitives are there. So you have implemented an half adder first, and now you want to reuse that half adder. So for that, you always require a structural modeling style. So you'll be finding, for most of the project that you'll be doing in a future, there are only two modeling style that we frequently use. The initial step will always be a behavioral modeling style, where we will be implementing subsystems, and finally combining all the subsystem is basically reusing the subsystem. So you require an understanding of a structural modeling style. So keep your understanding of both behavioral modeling style and a structural modeling style to a great extent, because they are the only two modeling style that you frequently utilize. Rest all are just for an information, and in fact we never consider them, so they are just for an information. So gate level modeling style is just for an information. We will never use them. In fact, structural modeling style also is very frequently used, because the final step when you have your top module, it will basically consist of a subsystem. If you are implementing a complex system, if it doesn't consist of various subsystem, then you don't require a structural modeling style. I guess this is clear, right? So whenever you don't know, the takeaway will be, whenever you start implementing the project, go with a behavioral modeling style. Do not look for another modeling style if it is a complex system that you are implementing, right? Memories. So memories been very difficult within Verilog. In fact, Verilog have very poor way of understanding a memory. So for example, how we consider distributed memories and block memories, how we differentiate them is, so if you consider an FPGA architecture, you have an LUTs, okay, and then inside an LUTs, or in fact inside an a CLB. So basic logic blocks are CLBs inside an FPGA. So they consist of two types of slices. Okay, so slice L and slice M. So slices for a logic and slices for a memories. Okay, so that slices can be used to implement a memory. So you have a slices which can be used to implement a logic function. Okay, and there are some slices which are being allocated to implement a memory. So whenever you are using that slices to implement some memories, that are called basically as a distributed memories. Okay, so if you are using an internal FPGA resources to implement a memory, they all belong to a distributed memory. So they are always not a good choice, because they will ultimately consume resources when you actually have certain memories that are available in an FPGA. So FPGA have some dedicated memories that are available, which are called as an block RAMs. So block RAM are the memory resources that have been dedicatedly available to use as a memory. So instead of using logic cells for implementing a memory, it is always a good choice that you start implementing something with a VRAM. So there is always a question that when you are writing a code, which memory will be inferred, right? So it is actually synthesized. So synthesizing basically means you convert your VHDL code to an FPGA primitives, okay, and then that will be finally implemented and routed on an FPGA. So you have written some code for an memories. Now how you'll be knowing that how it is inferred? So for example, the code that we have used over here, okay, so first code that we have utilized, right, that basically is a micro. So let us see what FPGA infers out of, right? So I'll just elaborate a bit, you'll have a good understanding. So I'll just go. Yeah. So now if I go to a schematic, and if I just zoom in a bit, so we'll be finding that it is a RAM B18E1. Okay. So RAM B18E1 is basically a block RAM, right? So the dedicated memory resources available with an FPGA are being utilized. So this is the efficient design. But when you write a code, and you have written some code for a memory, you may have an idea that how it will be inferred, whether it is a distributed RAM or whether it is a block RAM. And if you have utilized a distributed RAM, then you basically will reduce resources available to us. Okay, so whenever you are in this situation, always follow a language template. Okay, so language template give you a perfect representation of which type of memory will be inferred out of a code. Okay, VHDL do have very perfect way of representing a memory. So this is where VHDL actually leads Verilog. In most of the cases, you will be finding VHDL and Verilog do have same capabilities. But when it comes to inferring a specific dedicated resources for a memories out of the coding style, VHDL go ahead out of Verilog. Okay, but if you follow a language template, Verilog compiler will also try to do that thing, but that is bit tricky. Okay, so whenever you are in this situation, whenever you are in a situation where you want to implement a memories and you specifically want to infer block memory or a distributed memory for your memories, you go to a language template, you search for a RAM. Okay, you search for a RAM, and then suppose you are targeting a Verilog, so Verilog, go for a coding example. Okay, go for a coding example, and there inside a RAM you'll be finding three different types of RAMs are available. So you have a block RAM, you have a distributed RAM, and then you have an ultra RAM. So ultra RAM are available in an ultra scale family. So recent FPJ start to have this ultra RAM, and which are very big in size. In fact, they have very high bandwidth. Okay, but then let us assume that you have general purpose evaluation board. So they have this block RAM and distributed RAM. So if you want to specifically convert your memories to a block RAM, you go in there, you search for the type of RAM that you want. That is simple dual port. So you want to simultaneously read or write. Single port, you want to read at a time only, or you want to write at a time only, so you go with a single port, or you can go with a true 12 port. So let us assume that I want to go for a single port, and then write first mode. And in fact, we always prefer to go with the write first mode, since we do not read if we haven't written anything, right? And then here you'll be finding a good example, which is a bit difficult to understand at an initial stage, but just go for a logic. And here, this is the code. So if you want to generate a memory, you need to follow this type. Okay, so always at a positive of a clock. If enable is 1, if write enable is 1, then the memory instance that you have created, the address should be equals to d, and RAM data should be equals to D, else RAM data should be equals to address. Okay, so if you write your code like this, so if you just replace clock A with your clock, enable A with your clock enable, write A, or write enable with your write enable, memory instance, that is your array instance with a RAM name, address with your address, then you able to infer a block RAM out of it. If you want to implement a distributed RAM, you go to distributed RAM, and then you need to write the code like this. You need to exactly write the code like this, then only your memory that will be created will either have a distributed RAM or a block RAM that has been decided by a user. Okay, so this is how you implement a memory. So whenever you have an memory situation, if you are working with an VHDL, then you are at a good sites, because VHDL good language templates are pretty perfect. They lead to perfect creation of distributed RAM or a block RAM. But when you are in a Verilog, the first try to go with is a language template. You follow same coding style, but still if doesn't work, then the option that you have is you go with an IP. Okay, you include an IP, and then you try to reuse it. Okay, so we'll look at an IP examples a bit. Okay, next important thing is clock, because clock has been frequently required in most of the project that we always target are sequential circuits. Okay, hardly we able to implement anything as a combinational circuit. Something like barrel shifter we frequently do, but other than that, we always prefer to go with a clock circuits. Okay, so there are two categories of, yeah, anybody have a question? Yeah, yeah, no question. Okay, okay. So let us consider that you have a project. So first you need to, before actually understanding a modeling style, you need to divide your project. You need to categorize your project. So whether it is a data dominant project or whether it is time dominant project. So what data dominant project mean, or what time dominant project mean? So if your project specification consists of time specific value, for example, clock should be of duration of 10 millisecond, it should not be other than 10 millisecond, or enable should be high for 15 millisecond. It doesn't have a range of value. So what range of value means is, so if you are targeting on a DAC, a project like that, you have a range of frequency. For example, it specifies that the maximum sampling rate is 1.87. So anything below 1.87 is fine. So that is the range, right? But when we say that the DAC that I am using requires a data rate only 1.87, it will not work on any other range. So that is a time dominant project. And if it is not time dominant, that it have a range of a timing, then it is a data dominant project. Okay, so whenever you have a data, now this is bit clear. So for example, let us consider UART. So UART, you have you have, for example, variable baud rate. It can be 9600, it can be a different baud rate. Okay, so there you have a range of frequencies of an operation. So that is a data dominant project. If you consider a VGA project, so VGA project, the H-sync and V-sync signal that you generate, or a blanking pulses that you generate, have a specific time. So you cannot mismatch the timing. So in that scenario, whenever you have a time dominant project, you always go with an IPs. Now the advantage with an IPs and writing your own code. So for example, let us see, you want to create a 50 megahertz clock out of an 100 megahertz code. It is pretty easy. You require one counter variable. You just divide by 2. You'll be getting a 50 megahertz frequency. But then that 50 megahertz clock frequency will be delivered to your specific resources through a data lines that will not be delivered through a BubGIS. Okay, and you'll be finding there is slight mismatch between the clocking that the output device expect and the FPGA master creates. Okay, so whenever you have a time domain projects, you always prefer to go with an IPs. A simple example can be something like VGS. So whenever you have a VGS like project, you always prefer to go with an IPs. If you have a data dominant project, you can write your own code. So whatever coding style that you have learned, okay, that is valid only when your resource, when you have a heavy resources available on an FPGA. You do not need to use a micros or a primitives, or in fact whatever coding style that you have written does not consume much of the resources. In that case, you can proceed with an inference modeling style or the coding style that you have learned so far. But if you are in a situation where you want to have a time dominant project, there you'll be finding you always stick with either micros or a primitives or an IPs. You do not have much of the option with an infant. Okay, so this is how you divide a project. This you start to understand when you start working on a project. Okay, so these are the three methods by which you basically give and design entry to your Vivado. This we already looked, macros and primitives. Inference is whatever you have learned. Okay, just follow a good coding style and the basic construct knowledge, and you'll be ready to go. The third thing is IP, because let us assume that you are in a situation where you want to use an IP. How you basically utilize an IP, that will basically look. Okay, so I'll not actually consider a difficult example, because most of the cases professor always like to consider a simple example. They never took a difficult example, right? So I'll also consider a very simple example. So what I'll do is I'll basically create a 50 megahertz clock out of 100 megahertz clock. Very simple example. So to do that, you first go to an IP catalog. You go to an IP catalog. Okay, so here you'll be finding a whole lot of IPs that have been available for use, right? So I'll just search for a clock. So it have different types of clocks with an AXI stream and AXI master interfaces and so on and so forth. But we'll stick to very simple, which is a clocking wizard. Okay, so I'll just open this IP. Okay, we just need to understand, like for example, in a case of a micros also, what we do, we just have a template. We just understand how we use a micro. Then it depends on your application which micros will be using. Like similar way, primitives also, there are different, or there are large number of primitives. You do not need to learn everything. You just understand how you use the primitives. So if you have a certain application, you have a good idea that if this is the primitive I am targeting, so this is the method that I need to follow. Similarly, in an inference, you know a coding construct, just you need to keep the coding guidelines, and then everything is fine. The IPs also will be figuring out the same thing. So this is an IP that I have started. Okay, so here you can actually specify the input and output clock sources. I'll just keep this as it is. So clocking, you have a two options, so MMCM and PLL. So I'll request you to actually go through a data sheet for the specific libraries and look into a difference. So the major difference I always find between PLL and MMCM is whenever you require a dynamic phase shifting, that is you want to control a phase, we always use this mixed mode clocking manager, that is MMCM. And if I am least interested in a phase control applications, I'll always prefer to go with a PLL. Okay, and in fact you'll be finding here something is going invisible as soon as I switch between MMCN and PLL, right? So MMCM, you have a spread spectrum and dynamic phase shift. which is not available in PLL. And in fact, MMCL is just a modification of a PLL. Initially, we used to have a DCM also, but now it has been removed out of Envivado, right? So PLL. So this is our primary input clock, which is having a frequency of 100 megahertz. Output clock, we want a frequency of 50 megahertz. And then you can control the control pins that you have. So I don't want this two pins to be present in my IP, and then clock in and clock out, as simple as that. So let us just go to summary, click OK. So this will initialize an IP for you. Now the next part is how you can utilize this IP into your design. This is what we need to understand. We do not need to go through all the IPs that are available. We just looked at an application, search for the application specific need, be able to recognize an IP. Now, once we have an IP present inside this catalog, you just need to initialize your IP or configure your IP. So this is an instance that has been created. Okay. So what I'll do is I'll just try to utilize this IP inside an FSM. Right. So first thing is you can see this arrow over here. So you just click on that arrow. So this will basically maximize the amount of content that are present inside an IP. So you'll be finding there is something called as in Verilog source, which is clock wizard one. So I'll just double click on that, and here I want to reuse this, right? So I'll just copy this entire thing from module to this end, and I'll just go to FSN where I want to use this IP, and you already have an idea, right? So here just after a begin, so here parameter ends, and then you have an always begin, right? Yeah, so here what I'll do is I'll just after a parameter I just paste whatever I have copied. Okay, so this is the simple module or a top module code that has been present over here. I'll just go to an FSM, and here clock output, right? So this is the top module name, so I'll just copy this. Okay, the instance for my IP will be C1, and then I need to do a port now, right? So first port is this one, right? So I'll just paste it over here and dot, and here I'm using an explicit way of defining a structural model style, right? I'm not using an implicit way of definition. You can also go with a positional association or an implicit way of declaring a ports. So that is also fine, not a problem at all. Okay, so what I'll do is now I can delete this thing. I know that this is a clock out and this is a clock input. So for my module, the clock input is this clock. So I'll just add this clock over here, and let us just declare one variable which will act as our slower clock for our module. Okay, so temp clock, and I'll just copy this name and I'll paste it over here, right? And now as soon as I save this design, you'll be finding that our FSM will become a parent module, and then FSM will become our parent module. And if you just click on this arrow, you have a daughter module as a clocking design. Okay, so this is how you can utilize any IP that you want. So you just look for an IP, you configure an IP, and then you follow a structural guidelines. Okay, structural coding guidelines, and do not follow a positional association or an implicit way of definition. So what that means is, for example, let us see, I write a code by implicit definition, right? So I know that whenever I go to this module, the clocking wizard module, the first is an output port, which is a clock out, and second port is an input, right? So if I go to here, let us just name this as C2. Okay, and let us just comment this, right? The first port is an output which I want to connect to 10 clock, and then I have an input which is clock. So this is what we call as a positional mapping or an implicit way of definition. So software need to identify which port depending on the position. Okay, so this also create a problem in a simulation. So always stick to explicit way of definition. Okay, so always stick to explicit way of definition. Okay, so this is how you utilize an IP. Now let us suppose that you follow all the methods. So you have utilized an macros primitives, you have utilized the inference coding style that you know, you also have tried out with an IPs. Okay, but still you are not getting what you are wanting, right? For example, your timing is mismatch, your resource consumption is very high, or like so on and so forth. There can be various problems, but let us assume that you are facing a problem that your system is actually consuming a whole lot of good amount of resources, and that leads to basically a huge power consumption. So whenever you have a data centers, so their power consumption is also a need. So for if you are designing an application for a data center, you need to match the power rating. If you go above a power rating, they start charging an extra money for that, right? So you are in a situation where you have tried all this method, but still your power don't match to what the data centers require. Okay, so then comes the final way of designing it. Okay, so you have design already been placed, now you can adopt an Vivado strategy. So these are the some of the most unutilized thing that we have in Vivado. In fact, most of the engineers that we work on in Vivado do not actually utilize much of this thing. But then if nothing works, this is the final thing that always work for us. Okay, so I'll just give you a simple example how Vivado strategies work, and then probably you have an entire understanding of what need to do in specific situation. Okay, so for this case, I have actually implemented a RAM. Okay, so inference way of implementing a RAM I have targeted. Okay, so let us just go through a code. So we'll be finding you have this select or an output enable pin, then clock, write enable pin, address. Okay, so 11-bit address is there, then data in and data out both is having a size of 8, right? And this is the code. So here I have not utilized a Verilog 2001 guideline, like utilizing a reg over here and then trying to use the same variable that is result out over here, but instead I have declared a reg and then 8-bit. Okay, and this is an array, right? This is an array, a memory array of specifying 409520. So this basically signified is it is it is 11-bit, right? It is 11-bit. So this is the depth that we have in a memory, right? So the code is very simple, and this is how we target and RAM with an inference. Okay, so if write enable is true, so user want to write a data, so memory, then you have an address. Okay, so and then you will be feeding the data in inside that address, else you will be simply reading the data. So data out will be equals to mem into an address. In an Verilog, usually the code will not be that much simple, because in an VHDL, when you write an in standard underscore logic underscore vector, and when you are writing something like this where you are targeting an array, you need to first convert your underscore vector to unsigned and then unsigned to an integer, because in an VHDL array mapping can only be happen with an integer. With an Verilog goes ahead a bit. So here you can actually use the same data type that you have specified inside a module to map an element inside an array. Okay, and then depending on an output enable, so if output enable is high, so that signifies that user want to read a data out, else will be simply jumping into an high impedance state. Okay, so this is very simple inference. So I least care about what should be the implementation of this, whether it is VRAM or a distributed RAM and so on and so forth, right? So I just save my design. The first thing that I did is I set this as a top model, right? Now I perform run synthesis. Okay, so in fact this is the first time we are performing synthesis. Will take a bit of time. So till that time, if anybody have any doubt, we can discuss. Yeah. Yeah, synthesis is completed. So now what I'll do is I'll just open a synthesis design. Yeah. So now if I just go to a schematic, okay. So if I just go to, so here we have a synthesis, right? So if we just go to a schematic, we'll be finding it able to infer It able to infer out of a bad code that I have written. It able to infer actually uh, RAM B. Oh, okay, so perfectly it able to infer a block RAM, and this usually happens. So what happens is if you are writing if you are having a good amount of depth, so this is very high depth 4096. So usually Vivado like to use a BRAM instead of a distributed RAM. So this is a distinction point. Whenever you have a small depth, something like 128 or less of depth, you prefer to go with a distributed RAM because they are faster at that depth as compared to BRAM. But if you have a greater depth as compared to let us suppose 128, so if it is greater than something like 128, so 256 or above, you prefer to go with a BRAM because at that speed distributed RAM becomes slower as compared to BRAM, right? And here what I'll do is I'll report a power. So let us just report, and remember that report power required a constraints. Okay, so it should know, because for a power we need to know a clocking speed. Okay, so what is our clocking speed? Okay, so what I'll do is I'll just go to a source and I've written a constraint over here. So top.xdc, here I have created a clock which will have a period of 10 nanosecond, and then I'll be simply using that period for a clock. So this is a clock. If you remember, inside a RAM mux, I have the same clock as my entire synchronizing input, right? So before performing power operation, you need to specify the clock because dynamic power has been calculated on a clock, right? So I'll just go to a report power, and then you'll be finding power supply switching option. Inside a switching option, you will be finding a constraint clock where you have the constraint has been automatically inferred, that is 10 nanosecond, right? Okay, and now it will perform a power estimation. Okay, so you'll be finding the dynamic clocks, the clocks that has been consuming 20% of a power, right? And the confidence level is low. Now how you increase the confidence level, we'll discuss. What you need to do is you go to a simulation, and in a simulation you'll be finding you have a post timing and a post functional simulation. So you need to perform this too, and then you again perform report power, so that will increase your confidence level. Now confidence level low means you haven't feed any data to it and it has just been guessing what should be the approximate estimate. Okay, so here we have a 20% of a dynamic clock consumption. So one of the strategies is to, let us suppose, reduce this clock. Now there can be various strategies to reduce this amount of power, but let us 0.095 is very less power, and 20% we try to reduce this dynamic clock. Okay, dynamic power, let us just go to setting. Let us go to setting. Okay, so in an implementation you'll be finding by default you have this in Vivado implementation default report, which is a user defined strategy, and then you have certain parameter like you want to optimize design, you want to perform power optimized design. So by default it is actually unchecked. Okay, so it is not enabled by default. So before starting a session I have enabled it actually just to test the code. So, and then you can have a place design to match a timing requirement. You also have, after implementation, if you want to improve a timings, you have this post placement strategies. You want to remove a congestion or reduce a congestion, you have a route design strategies, and so on and so forth, right? So I'll just do a power optimizing strategy over here. I will just apply, perform. Okay, okay, so right now my power consumption is 20%. Okay, so without changing the code, now let us just perform an implementation and let's see whether Vivado actually able to reduce our power consumption. Okay, so for this, if you want to explore more, what are the physical ops strategies, what are the place route strategies, you refer to UG904. Okay, so UG904 is the best reference that we have. UG904, you can simply go over here and then you can understand how you can use this different implementation strategy. Okay, I'll just looked into whether we can reduce our power with this design, and then we can conclude. Okay, so probably this will be our final demonstration. This will take a bit time because our design is actually been implemented on an FPGA architecture. So after this, only the last step that remains is generate a bit stream, after which you can actually program an FPGA to see your design working. Okay, so it will perform both placing, routing, and implementation. And this is one of the simplest implementation strategy that we often utilize, that is power optimization. Place and route we always use, that is place optimization and route optimization uh, uh, when you have a mismatch in end timings or when you have a congestions. Okay, so that basically reduce the congestions. Now we just close our design, we go to implementation. Now we just close synthesis, we go to an implementation, and inside this we will now report a power. Let us see. So initially we have a 20% of a power consumption with a clock. Okay, I'll be finding, I'll just try to report a prop. You'll be finding it automatically have reduced it to a 15%. Okay, and you'll be finding from a 4% dynamic power it have reduced to a 3%. So this is without changing the code. Okay, now you'll also understand that it have made some changes, right? So for that reason, like, you'll be finding that after synthesis these two options are enabled, and after implementation these two options are enabled. The reason being, when we adopt certain implementation strategy, it basically changes or adds or reduce certain component, and then it becomes necessary that you verify that it is working fine or functionally correct, and the timings are also matching. Okay, so this is how you perform an implementation strategy. For a synthesis strategy we always use, so for example you have an FSM. Okay, so for an FSM, you either follow let me just show you. So this is, we are inside a synthesis. Okay, so here if you just go to an FSM extraction, it is by default auto, but you know that one hot consumes greater resources, but they are simple to utilize. Then you have a different strategies for an FSM extraction. Okay, so we usually for a synthesis we prefer what FSM to be extracted. So whether it should be a one hot encoding, sequential encoding, a Johnson encoding, Gray, or an auto encoding. And the second thing we frequently do is gated clock conversion. So this basically is used to reduce dynamic clock. Okay, so this you can also explore by just googling Vivado synthesis strategies. So UG exact number I don't know, but for an implementation strategy, I'll recommend you to go with UG 904. You'll be finding an entire details. And for an synthesis strategy, you simply Google Vivado synthesis strategy. You'll have a good document on it, and you can just refer to it, and you'll be finding a good idea. Okay, so this is how you proceed when you don't reach to what you are expecting out of this three method. Okay, so this is what I wish to share with you. Probably this is how you enter into a design, and then this is how you optimize the design. Other thing is, I do have some courses on an Udemy. So if you want to further learn Verilog, VHDL, or a system Verilog, I'll be happy to share a free coupon code with you, so you can also learn fundamental things if you want to, right? So those who wish to actually enroll these courses for a free, you can simply email me, or in fact you can ask my email ID or a number from Rathod sir, in fact. And we can Rathod sir do have some courses, so we both have some courses. So if you want to learn Verilog and VHDL further in a bit detail, quite heavy courses, so you can request for a coupon. I'll happy to share the coupon. That's it from my side. Rathod sir.
Very nice, sir. Done. Thank you very much. Thank you, Kumar sir. Thank you very much. Shall I take out the presentation mode from your?
Yes.
Done, na? All question
Yeah,
answers done, na?
yeah. Anybody have any question? So I'll like to answer any question if you have. Yeah. Yeah. Okay, sir. Yeah.
I think nobody has a question.
Is it a open source?
काय मॅडम ओपन सोर्स काय व्हॉट
वाडो ओपन सोर्स मध्ये अवेलेबल आहे का?
नाही मॅडम झायलिंगचा प्रोडक्ट आहे ते परचेस
ओके
करावं लागतं.
ओके ओके.
But ma'am, we can have so if you want to explore, you have a web license that is freely available.
Okay,
अच्छा.
okay,
Yeah.
okay,
Yeah.
okay. That is good. It
Yeah.
was nice, very nice,
Yeah,
nicely
thank you.
organized.
Kumar sir,
Yes, that was.
thank you very much. Thank you very much.
This,
This is a memento from our side and your certificate.
yeah, so what
Okay.
kind of picture which is a promotion?
Very nice. So thank you very much. And 2 hours evening. And for thank you to you and thank you to participants both.
Hana. I can
Gopal,
understand
thank you very much.
participants.
But we don't have any choice. But I have seen your feedbacks, and probably in next workshop we will take care of timing schedule थोडं कमी करावं लागेल असं मला
Yes,
वाटतं. Each
yes,
for all, but it is okay. Very nice. Your session was very good. That is important, and I hope today's sessions you enjoyed all sessions. Correct. So anyway, we will meet tomorrow. Shaila ma'am is there tomorrow. Her
Yeah.
session is there in the morning, and then evening again Naushad sir will be there. So and then after Naushad sir, then the next day will be Saturday. Saturday morning we will have an assessment. We will see how to do that, and then we will have a validity at 2 o'clock Saturday. Correct. So this is how our next plan is. So thank you very much. We will meet tomorrow morning. Thanks. Kumar sir. अरे कुमार सर गेले की काय? Okay, thank you everyone. You can now leave the meeting. Participants can leave the meeting, please.